Bienvenidos a este tercer día de ICASAT, disfrutando la conferencia. El día de hoy tenemos la directora de la Universidad Mourshed, a cargo del profesor Ravela. Comienzo con un poquito de entonces, en preparación a la plática del día de hoy, me puse a indagar cuando habíamos hecho el primer contacto con el profesor Ravela. Fue por allá por el 2012. Y una cosa curiosa es que me puse a ver cuál había sido el primer mensaje que le envié y cuándo lo había enviado. Entonces resultó que lo envié el 4 de septiembre, pero lo curioso es que fue a las 9:04 de la mañana. Entonces eso me llamó mucho la atención. Entonces llevamos ya 13 años trabajando. Y otra cosa que me dio curiosidad por hacer, en vista de la intensa relación que hemos tenido a lo largo de estos 13 años, es cuántos mensajes de correo electrónico nos habíamos enviado. Entonces, chequé en mi cuenta de Gmail y en estos 13 años encontré 5.263 mensajes. Si dividimos el mensaje entre los años, resulta ser que por año nos hemos mandado unos 404 mensajes, un poquito más de un mensaje diario. Pero eso no toma en cuenta otras cuentas de correo, los mensajes en Slack, o ya más recientemente WhatsApp. Entonces, esta relación que hemos mantenido ha sido muy intensa y estoy muy agradecido porque creo que me ha hecho crecer mucho profesionalmente. Y en eso pues estoy muy agradecido y quiero agradecer la presencia de aquí en ICASAT 2025. Entonces, ahí es el investigador principal en el Departamento de Ciencias de la Tierra, la atmósfera y los planetas en MIT. La atención de SAI se centra particularmente en temas de aplicaciones que involucran la vida, la. Por ejemplo, en este contexto, él colabora, por ejemplo, con Sarah Seeger, y si ustedes han escuchado acerca del descubrimiento de exoplanetas, ahora la búsqueda de exoplanetas que tienen vida, ahí pueden ver el trabajo de SAI. Sus desarrollos luego también se relacionan con huracanes, precipitaciones, inundaciones. Ahí colabora con Kerry Emanuel, que también es la autoridad mundial en términos de huracanes. Nosotros, en particular, SAI y un servidor, junto con otros, hemos trabajado en temas que tienen que ver con la identificación de animales, identificar al koala sultanito, el koala americanito, con otras personas. También hemos trabajado en inundaciones. Y me acuerdo de las aventuras que tuvimos volando drones, cuando no era tan común, en el Parque Nacional de Iztapopo. Y algunas cosas se ven reflejadas en el Politécnico, en ICASAT, por ejemplo, el Fab Lab que tenemos en el Politécnico, el primero del Politécnico, fue inspirado en sus ideas. Entonces, puede ser que SAI se mueve con mucha agilidad en muchos campos, ¿no? Algunos que tienen que ver con datos, teoría, y también expertos humanos, de los cuales veremos algo en su plática. Por ejemplo, ciertamente es algo de indicativo, ¿no? Pero su oficina en el Green Building de MIT está a un lado, o sea, lo blanquean, la oficina que fue de Edward Lorenz, el creador de la teoría del caos, y al otro lado la oficina de nuestro Mario Molina, el premio Nobel de Química. Pero los intereses de SAI son muy amplios, incluyen aprendizaje, estimación, control, cuantificación de incertidumbre y la toma de decisiones. En eso SAI aborda los problemas mediante el uso tanto de física como de estadística. En ello entonces se enfoca en entender los riesgos asociados a los peligros naturales que surgen del cambio climático. También estudia la construcción de agentes autónomos, como observadores estratosféricos para el estudio de eventos extremos. Igual aprovecha este enfoque entre la estadística y la física para reducir las ecuaciones que gobiernan la dinámica de los fluidos. Entonces, en pocas palabras, se enfoca en avanzar las ciencias de sistemas para investigar la Tierra y su ambiente. SAI tiene una tremenda vocación hacia la enseñanza y es palpable en los cursos que imparte. En particular, hay uno que literalmente nunca terminan. Ustedes pueden tomarlo hoy, tomarlo dentro de un año y siempre se ven cosas nuevas, siempre se ven cosas interesantes, cosas de avanzada. Y por cierto, Sai es profesor invitado del Instituto Politécnico Nacional. Él imparte sus cursos desde donde quiera que esté en el mundo y hace espacio para transmitir sus cursos en videoconferencia. En este semestre, por ejemplo, está impartiendo clases que toman varios de nosotros, lo tomamos los martes y los viernes. Entonces, así desde cualquier parte del mundo que se encuentre, transmite su clase. Y hoy tenemos el privilegio de tenerlo con nosotros en persona y nos da mucho gusto. Entonces los dejo con Ravela.
Hello everyone. I'm glad I didn't understand a lot of what you said in the video recording if I did. But thank you for that wonderful introduction. Okay, my name is Saira. I'm going to talk to you today about a few ideas. And these ideas are going to be tying climate to sustainability. We've heard a lot about sustainability, we've heard a lot about climate, one way or the other, but the two haven't been connected because climate is about looking ahead as much as it's about experiencing. And our notions of sustainability in life. Today I wanted to walk you through a few ideas that turn out to be really key from the perspective of climate and sustainability. All of you see this beautiful photograph. Joaquin was a member of my group. We worked together, collaborated for a while. So we had a great time. I hope to continue that conversation and collaboration moving forward. Now, before I talk to you about climate and sustainability, let's talk about risk and resilience. The right way to think about this comes from the insurance world. Insurance people are very used to risk. Every time somebody's car gets in an accident, they have to consider the volume of accidents. So when we think about risk, we should, including the United Nations and ICASAT, have adopted this view. There's lots of ad hoc, ways of thinking about risk, but the way we think about risk is shown in that diagram. It consists of hazard, exposure, vulnerability, and the intersection of those three that determines risk. So what is a hazard? Hazard is an external event like a cyclone, heavy rainfall, heat stress, and hazard have probabilities. Most people they think about hazard, they think about what's going to happen next. But when we think about hazard, we think about the distribution. How frequent are they? How severe are they? This is the part where climate science tries to do most of its work. In producing these risk assessments, these distributions that quantify the hazard, especially when the climate is changing. What would the hazard, what would be the cyclone distribution in 2050? That's a question for climate science. Now, the second aspect of this is exposure. Exposure is about assets. People is about what is exposed to the hazard. If you're an insurance company, you might look at people exist in a particular town or city, how many buildings might exist, how much transportation might exist. The third, perhaps the most difficult, is vulnerability. The age of equipment, how old is your bridge, how vulnerable is it, how fragile is it. These are aspects of it. While hazard is easily amenable to climate science, the other two are not so. They're very, very difficult. Together, combine these three to get risk. And then we design interventions. Maybe you want to build a big seawall to protect your coastal community. Maybe you want to put your houses on to save from flooding. Maybe you want to build elevated expressway to protect yourself from rainfall. All of these are aspects of interventions. And we design these interventions and we think of a system where we put these interventions back into a simulated world to reassess what our risk is, and eventually we come up on a plan that's executed. That's the framework that we're talking about. This has become increasingly important as climate is changing because we no longer can rely on mitigation alone. We're probably going to blow to 2 degrees Celsius, reach 3. And at that point in time, a lot about our world is going to change. So the world will need to adapt. What I'm going to focus on is adaptation and how that. Okay. So let me take you first to Thailand. I'll take you on a worldwide tour of a few places. We'll go to Thailand. So this is a very recent event in the Nan province where Cyclone Wifa showed up. And you can see its track. It comes from the north of Thailand, so Laos. And by the time it reaches Thailand, it is not very strong. I mean, for us in the Gulf of Mexico, we have much stronger cyclones. This was not even category 1. But what was interesting is because of climate change, the rainfall system intersected the cyclone. Usually we don't have rainfall in cyclone. The cyclone season, there's the rainfall season, the two systems are very distinct. But here they intersected and it caused havoc, producing a 140-year event. So Thailand also has many other hazards that are right. So this is a very good example. So how do people do it today? How do you think about all of this and design a system? The first thing people do is they rely on observations. So here on the left, you'll see an animation of the amount of flood. Blue means it flooded, white means it didn't flood. Every year is clicking down here, you can see there, and you can see how much flooding is happening. Now in the middle, you see a panel of the return period. Dark blue means flood is very frequent, blue means flood is unfrequent. This is what we mean by hazard. You can do this, by the way, if you're a student or postdoc, you can open your laptop in the next 15 minutes, you can go to Google Earth Developer Engine. It takes 10 minutes to write this code. Very fast nowadays, you can get very high resolution assessments of what has been happening. Okay, and you can also determine exposure. Nowadays, we have a cool idea, which is to look at the amount of nighttime light activity. A lot of authors have worked on this issue. So by nighttime light activity, we mean that how much electricity is being consumed as visible from nighttime light. The more light there is, the more people there are. So you can use this to determine what the exposure is. And you should notice in this map that this is Bangkok, Seoul, Thailand. We don't have similar things for Mexico yet, but give us 6 months. So if you look here, it gets more and more red or yellow, precisely where the hazard is. It's not like people go into far-off places and live there. They live where the hazard is. Why is that? Because people like to live next to water. They live next to rivers. And so there's a very, very dangerous intersection. But again, all of this is in present time. Now let me come to the third part, which is vulnerability, which I mentioned earlier. Here on the left, we want to find out. For example, if you go to Mexico City and somebody asks, what are the most vulnerable parts of Mexico City? Similarly, here we're asking in Thailand, what are the most vulnerable parts of Mexico? How would you determine something like this? It could take you months of analysis because it's not all about the elevation of the land. It's about buildings, it's about urban environment, it's about pipes, broken pipes, it's about choked streets, it's about people being in the wrong place at the wrong time. This sounds like a nightmare. So how do we get vulnerability assessment has been an enormously hard problem. One of the breakthroughs I think that has happened is the use of large language models. What we did was we built what's called a retrieval augmented generative model, so a RAG on top of a large language model. Simply put, what we did was we collected all the newspapers from Mexico. Similarly, you could collect all the old newspapers from Mexico City. Not only newspapers, you can collect poems, you can collect songs, You can collect movies. You can collect news articles. And in that information, you get an understanding of how vulnerable. In that information, you get an understanding of how vulnerable Bangkok is because every time something breaks, it shows up in the news. Every time something goes wrong, it shows up in the news very fast. And if you look at these news articles, you start which city are more vulnerable than the others. Very easily. In fact, what would have taken us probably a year, maybe 3 years to do, took us 3 days to do using LLM. So I'll show you now an animation. So this is actually accurate. These are the most vulnerable regions. And not only can we do that, if you follow this video, you can see why they are vulnerable. You can diagnose, you can go back and say, you told me this is the most vulnerable region, why is it the most vulnerable? And it will show you all the information you collect and tells you in bullet points why it's wrong. This is an amazing tool to have, to be able to use AI in this manner. Similarly, we can do a lot of satellite to extract exposure, but vulnerability has been a hard piece. Now we have to not many people use it this way, but this is how we can get all of this information. Nobody typed it. There is a knowledge graph that gets produced by finding all this information from newspapers through an LLM and putting a retrieval model, which answers questions. What's the most vulnerable part of Mexico City? Why is it the most vulnerable? Here comes another answer. You can verify. You can go and look, and you can see which articles that inspire you, where you're telling us. This kind of vulnerability analysis is new and different. Not only can we do something like this, we can go backwards. Here, for example, we're looking at Bangkok Airport. And if you were to ask why it's vulnerable, you'll see that it is related to a few key things. So, if only 1.5 meter of flooding happens, it trips the diesel backup. Once the diesel backup trips, all of the airport is gone. The pumps don't work. So this type of analysis, what are you supposed to do with it? How many people are you going to call? How much GIS data are you going to get? How are you going to build this? But when you look at newspapers, if you go to rural areas, like I'll talk to you in a moment, people tell you ancient stories about how a major event happened, what it did to the people. We codify these experiences of pleasure and pain and song, music. All of this is now accessible. Rather than be an engineer, be a social scientist. You'll understand vulnerability much. Okay? So that's some advances in AI calculators. I'm going to take you to a different part of the world, Bangladesh. Bangladesh is in a very hard spot, and I'm going to focus on southwest Bangladesh, which is where those golden squares are. This part of Bangladesh is interesting because in the south you have the Bay of Bengal, and all the shading are watersheds. At the bottom you have the mangroves and sundarbans. And those white enclosed contours are called polders. These are embankments, closed embankments within which community lives. Now let me tell you why this is so hard. Here, what has been happening is that because of these embankments, and this is the coastal delta, right? Lots of countries like Philippines. This coastal delta means there's lots of channels coming in. What that means is that when there's high tide, the tide comes in. Usually it just floods the land, it's tide. Because of these embankments, what happens is that tide goes up the channel much further. And the tide is bringing with it salt water. It's not fresh water, it's coming from the ocean. So the salinity is going much further north than it should. From the north, we're supposed to get fresh water from India and from the Brahmaputra, from Ganges, from Ganga, but you don't get it because it's a dam. Close, which means fresh water is missing, salt water is missing, and the balance of that boundary, the salinity boundary is going much further in than tidally amplified. This is the normal situation. So the soil has been salinized quite a bit faster than it should. What's even more worse is that because of these boulders, the land inside is subsiding. But the rivers outside the land is rising because where will all that silt go? The silt has nowhere to go but to pack the river. So this balance is getting worse. Now, when rain falls, because of this head, there's no room for that rain to go. It waterloses. Also, because they've been growing rice, many other crops, they've been taking water out more than they should. As a result, the groundwater aquifers are being filled by salt water. So now when the rain comes, the rain has no way to displace the salt water. The salt water is much heavier. And the rain then just stays and waterlogs. So not only is the water table high, it's still. Now we have a waterlogged land for which water doesn't go out easily, not easy to pump out because of this. And which means if it's in the early rising season, great, we love the waterlog. But if it's in late season, it's a disaster. And against this background, this is already a very buggy, complex situation. You know, there's salinity that's creeping in, there is waterlogging that's going on, there's not enough water because it doesn't fill the aquifers. So in the drought season, there's no water. And moreover, now comes the cyclone. The result of the cyclone comes. Because there's a polar, the cyclone brings an enormous amount of salt and it dumps the salt water in the cyclone. Because they're not well made, they're not high enough for many reasons. Mostly it's because they're not well maintained. So this water comes in and deposits salt water, which means what was a fresh agricultural farm where they grew rice? For 8 years, that water stays and the salt doesn't reach out for 8 years. Can you imagine living in this world? Now, climate change in your system. As climate changes, the sea level is rising, which means there's even more stress for salinization. The number of cyclones may not be going up much, but their severity is going up, which means suddenly we have an amplified disaster story in the Sylvian flush. When we think about sustainability, we think about these kinds of problems going forward and what to do. The situation is desperate. People have gone from being able to do agriculture to mainly aquaculture to shrimp farming. And the problem with shrimp farming is it's capital intensive, but it's not labor intensive. So somebody who has a lot of money buys these farms. The people who had 1 acre lots now are indentured laborers in their land. They lose their land to someone else. Saltwater shrimp farm. Somebody's making money outside. These people that get on a boat, India, or they go to Dhaka, where they work, or some people kill themselves. Okay, so we are interested in these kinds of hazards, wind, storm tides, rainfall, and flooding, but we're also interested in heat, other things, but this is what I'm mostly focused on. I mentioned use salinization. Take a look at this picture. This picture shows you how salinity has been changing. This is soil salinity of the topsoil. So we're looking at agricultural productivity. It's for a particular land use category. And if you look at red means it's about 3 deciments per meter, which means you can't grow rice. Rice requires much less. You can maybe grow watermelons, but not wheat. So you can notice as this loop plays on the top, you'll see the year. But as this loop plays, I'll take one more. I should make my chips. Okay, as you can see in the bottom, in 2014, nothing was going on. But by the time it reaches 2025, the whole thing will go red. Our prediction is that the number of people living in this part of so the Sundarbans are down here, and Bay of Bengal is here. There's a lot of people living here. It will not be excessive. We cannot do any agriculture here. That's the climate disaster we're looking at. But again, I want to point out that this is all the past. I mean, this salinity map that you can get is very easy to write code for this machine learning out. And then you just grab Landsat imagery, we actually take in situ measurements using what we call an informative observatory, where we constantly monitor and look for where we should take subsequent measurements to maximize information gain. So with very low cost, people in schools and other places going out there and taking measurements, we can keep a continuous monitoring system. But that said, this is still about the present. But I don't think sustainability can be done that way. Imagine I were telling you the story, looking down and walking. You will be very nervous by the time you got to the edge of the road. You will be nervous about how I'm. You just look a little bit ahead. Into the future, everything stabilizes. Really simple thing. Want to smooth your transition, you'll be able to look ahead. And I'm going to tell you more about that in a moment. But we've been working with the community a lot in trying to enable this decision making under these complex set of circumstances I just told you about. On the top left are a group of people in a village called Ashashani, where we've been working. In the bottom left, you see me and my team, and some very good friends we've made, and we hold sessions, day after day after day, where we build games, snake and ladders, Ludo, and the person plays this game. Every time they make a move, they encounter an event like nature. Maybe they encounter a cycle, maybe they encounter a heat wave, maybe they encounter a bad road, and when they do that, they lose some money in what they've invested in agriculture, aquaculture, shrimp farming, or some of these other professions. Every event costs them some money. We monetize the game, which is easier to play. And their job is to find an investment strategy against nature's threats that are being stimulated. And these stimulations are being made by hazards we've produced, projections we've created. And we keep simulating. And then they play this game, and if they survive, either individually or as a community, they've found a sustainable strategy. They found a sustainable strategy to adapt. This gaming process has been, for us, revolutionary. It does so many things at once. It engages people because people love to play games. You go into a village and start playing Ludo with them, they'll all be drinking lemonade and playing the game all afternoon. It's a great engagement model. Second, it's a very democratized model. Everybody has the same voice in this story when they play the game. Third, it transitions people from very fatalistic thinking, what will I do next season, to risk-based thinking. Oh, what if a cyclone comes next season? What if it goes up? Should I buy insurance or should I not buy insurance? Should we make it common? It transitions people to risk-based thinking. It allows them to identify gaps. For example, if they want to build a managed aquifer recharge system, or a solar system, or an agrivoltaic system, it's a lot of money. They identify these gaps, and we can bring other players into the game, like a bank, or an NGO, or a government official, into the game setting. We build software around this, and the way it actually works is people communicate to us among themselves a graph that indicates their story. We're facing a waterlogging problem. Okay, well, rainfall causes waterlogging, something else happens. So they build a story that's very particular to their community. And then they turn the switch on and stimulate this graph. Here comes a cycle. What's going to happen to you? Then they design the investment strategy, intervention strategy, optimize it. Simultaneously, in the background, we have been working with building machine learning tools. He is actually one of the various, one or one, maybe he might not here, but Joaquin and one-on-one have been looking at reinforcement learning, for example. That's one approach to do it, stochastic dynamic programming, and the approach to it. The many approaches where the compute. And if you look at this here, there's all sorts of people. There's two sides of Ravela. The one that's making a lot of money is my algorithm. So you can, in many iterations, come up with good strategies for the community. So I want to now communicate to you our signals and systems group version of the computational climate sustainability stack. At the top is the hazard, which I'm going to talk to you about next. After that is the exposure layer, where we use any number of tools, in situ to remote sensing, to drone sensing, to where we minimize the cost. You know, our whole salinity observatory in Bangladesh costs $4,000 a year. Pretty cool for about, 1,000 measurements. And it's actually quite low cost. And then determining vulnerability using AI that collects information about the people, from the people, of the people. And we build that into knowledge graphs. Then we do impact assessments through such graph that we build with the community, and then we let them optimize their interventions by playing. It's local, it's democratized, and it is, we've applied this in Thailand, we've applied this in Bangladesh, we're applying it in Thailand, we applied it in Bangladesh, and we are planning to apply it in India, and we are hoping to do the same thing here. It works out. So, I hope I'm clear on what we mean by enabling sustainable decisions. But I haven't yet talked to you about climate change. I've only said as if we're doing it today, under today's climate, under today's assessments of vulnerability. The vulnerability and exposure are very hard to assess in the future climate. How would you tell me what the salinity is going to look like in 2050? Sounds very difficult. Data-driven approaches don't really work there. You need some notion of physics to be able to do something like that. How would you determine what the exposure will be in 2050? Maybe you can. Maybe you can project the growth of nighttime light activity to 2050, but that's also limited. So what we do is conditioning. Meaning, we look at some things that we can change as a function of climate. Most highly the hazard, and we hold the others steady to today. But even that little change of what happens when the climate changes is sufficiently alarming that we ought to think about how we make sustainable decisions. If we could do all of them, the story gets much, much more. Okay, so now let me turn to the next aspect of climate. It's the big elephant in the room. Everybody says climate, but they don't really think about oncoming climate. So, IPCC has done a great job, as much as can be done, to quantify. Here, for example, you see the mean temperature around as it's been rising, it's a very standard figure. Under various scenarios, SSP1 being benign, SSP5 being very aggressive. In terms of climate impact, it tells you what the change in temperature is. And this temperature means something to us. 4 degrees Celsius, most of this planet won't exist as we know. Our ecosystems will fall. So we look at these scenarios. The first thing we say is, how do I change it? You don't. So immediately when we go into the future, uncertainty starts to come. In the past, I don't really think about it. Those uncertainties are just measurement uncertainties. Scenario uncertainty. And many climate models which simulate the Earth's climate system are used to this. They all have their problems. There is no perfect climate model. They're all imperfect. Their uncertainties come. So even though they are subjective uncertainties, we want to go out in the future. The other thing I want to point out is even more critical. On the right, on the left, you see the second graph. These blue dots are the number of cyclones we've seen over Bangladesh over 30 years. So the most intense cyclone has a wind speed of about 140 knots. Since it's about 30 years, your instinct is to say, we get 140 knots in 30 years. 30-year return period. That's how you think about it. But it's totally wrong. The return period could be less or could be way more. In fact, you observe so few cycles that you cannot assess the return period. You need many more, much more data to be able to say something on it. And that uncertainty, if you use rank statistics, you can estimate that little teal or whatever color line is there. You can go from 1,000-year return period down to, maybe 5 or 10-year return period. 3 orders of magnitude change. is possible. So even in present climate, for rare extreme events like cyclones that have not been that many, it's very hard to estimate what our risk. This is not just about the future where there is no data. It's even in the present where there is such little data that you can't do much about. This is why we're going to do what we do next, which is to think about how is it we're going to quantify the risk in terms of the hazard. How are we going to do it? We can't use observations. Observations are important, but they're not nearly enough. In AI, we love to use data-driven methods. I'm sorry to tell you that. Even though I have my background also, it does not even come close to quantifying the risk that we need for the most intense things that are happening. I mean, the rarer it is, the harder it is to quantify. This is the world we live in, and quantifying this risk is extraordinarily important. I'll tell you more about that. You know, if you really want to know how to protect, for example, Bangladesh or Bangkok or Mexico City, it's not the average mom and pop rainfall that you should be caring. It's what's happening in the tails. Those extreme events, one comes, wipes out the city. The damages that you incur there are so economical. That's what you should be protecting yourselves about if you want to protect cities. For a long time, we've been worried about the average or the expectation, but we really should be more risk-averse looking at the tails. But this is very hard to do. So I'm going to take you to a few different ideas, being mindful of my time. Great, we have a bit of time. So I'm going to take you through two ideas that we're going to do. The first idea is, when you want to resolve these extreme events like a cyclone, your instinct is to say, oh, let's build a very high resolution model of the atmosphere. You know, let's build a model that 1 kilometer resolution and beautifully simulates cyclones. The problem with this type of story, and it doesn't have to be just be cyclones, it could be extreme rainfall, it could be extreme heat waves, it could be heat islands, all sorts. The problem with this type of story is the amount of computation power needed to do these simulations. And if you want to quantify risk, you have to do hundreds of thousands of these things. Where in the world is the energy to do this? It's simply not there. Climate models, on the other hand, which I can define, every organization has a climate, whether it's GFDL or UK, and they don't have a resolution. The resolution is too coarse. At 50 kilometers, you think you'll see a cyclone that's about 100 kilometers wide? 25 kilometers. But 25 kilometers is as good as it gets today. Many climate models are at 100 kilometer resolution. So climate models don't simulate these extreme events. They're not meant for it. They're meant for giving you information about the averages. They're not meant for you to give you about the extremes. But this idea that you will somehow just use a detailed model and get it over with. So what should we do? These detailed models are supposed to be physical. Is there something clever with it? The arc that I'm going to paint now is one, yes. You're clever about the physics, you can do something, and the example I use is of a cyclone. Or two, you don't have to be that clever if you use just a little physics and just a little machinery together. That's the second part. And both of these will turn out to be a beautiful way for us to make progress on resolving extremes and quantifying the hazard from extremes and connecting it with the rest of the story, exposure, system. So let me talk to you about a method that we've been using. So we came up with this method to do simulate cyclones from climate models. We call it downscaling, which is the cyclone. The climate model doesn't have any resolution, but we downscale, meaning we add the resolution and generate these cyclones synthetically. The technique that we have is purely physics-based. It's probably the only known method in the world that is so successful. It works where there is no data, it doesn't require you to get any information about the past cyclones. And it works really well where cyclones were well observed. And I will just show you what we can do with it. So I will skip this slide. It's based on a very simple idea that a hurricane is a Carnot engine, refrigerator. It's a heat engine, and the rest follows. We'll skip it. But one of the things that comes up as a result of doing all this is actually very simple math, by the way. Is you can simulate hundreds of thousands of these cycles that are not real at all. They simulate what type of cyclones you can face in a particular climate. And we've been doing this in the Gulf of Mexico, Indian Ocean, the Western Pacific, every basin basically. So once we can simulate these cyclones, we can assess risk. Let me show you some examples. So here we can simulate cyclones, and from the cyclones we can get distributions of wind speeds. If you know how windy it will be, what the distribution of winds in present climate in blue, and future climate in red is, you can figure that out. You can figure out how rainfall is going to change in a climate scenario. From these two, you can figure out how floods are. So here's an example of a simulation I'd like to show you. So here's a cyclone coming in, and the cyclone then causes flooding. So this is tide, storm tide coming in, and you can see the little wind vectors coming up to Bangladesh, and we can do this kind of simulation anywhere. So we can take this novel technique to produce cyclones where climate models don't produce it in any particular climate scenario. We can take that, tell you what the extreme winds are going to be, what the extreme rainfall is going to be, what the storm tides are going to be, and our storm tide simulations really match observations quite well. Here, for example, I show you how they match the observed records, and we incorporate sea level rise projections. So when you have sea level rise projections in the future, our techniques incorporate those, and I'll give you the punchline. This is the first known assessment of coastal flood risk in Bangladesh under different climate scenarios. In gray is the present climate, in red is the future climate. Machinery, taking a climate model, producing a lot of cyclones, climate model prescribes, taking those cyclones, driving flood models, under sea level rise, tides, all of this story, and eventually you get to what the flood could be. And this difference, if you notice, every one of these graphs is a very robust result. The 100-year return period in present climate becomes like a almost 10-year return period in future climate, which means what happens once in 100 years now will happen once in 10 years in the future. When we presented this result, the news exploded. And that's the risk evaluation basically. Do we have such estimates from Mexico? We should produce one. We have the technology to do it. But I will skip these. And I want to talk to you about how this is even possible. The traditional method is in an efficient way. Is you simulate a cyclone, simulate storm tide, simulate flooding, and you do lots and lots and lots of simulations. And then you say which one was the most intense one. It's a total waste of time, you know? You do 10,000 simulations and you do 10 very intense ones. And you avoid it. And you have a system where you say, give me a really strong cycle. You don't have to do all these simulations. Machine learning enters the story where we use a technique called active learning. And so if you don't do it, you get this very slow performance improvement as you keep training an algorithm with more and more data. But you never get to a point where you say, give me a cyclone that will cause a 3-meter damage. You have to do tens of thousands of simulations before finding out. Let's not exaggerate, thousands of simulations before you find one that causes a 3-meter damage. Because 3-meter damage is so big. We want to be able to simply say, hey, 3 meters, you're 3, which looks like this. Give me a shot. And every time you say, give me a shot, it gives you the precise shot that you're looking for. You don't have to waste a whole bunch of computation. Can we do it? We can. We use a technique that is based on retraining surrogate models on the fly using online learning. And the detail is not interesting, but the amount of efficiency that you get because of this is that by the time you look at only less than 20% of the data, you're starting to say, give me this damaging cyclone, just stick your hand in the bag, pull, get a damaging cycle. Give me a damaging cycle, and I get a damaging cycle because of this process. Otherwise, you stick your hand in, you get no. Throw it away. Use it 1,000 times. Okay, maybe I found one. So there's very efficient sampling processes that we have built that enable us to be able to actually do risk and hazard assessment. As a result of this, we can study flooding. So here on the left is a simulation of a storm tide coming in Bangladesh. And we can do that for cyclones. We can do that for rainfall. Here's happening what happens when rainfall falls. About inundation. And we can do compound flooding that involve both. And this is the frontier of flood risk assessment. Okay, I want to talk to you about one more piece of technology because I said earlier that we are interested in looking at physics, but also machine learning. And after this, I will stop. So I want to start by talking to you about this graph. It's about extreme rainfall. It'll take me a couple of minutes to explain this graph, so please try to follow with me. The x-axis is called return rate. So 10 power 0 is 1, 10 power 1 is 10, 10 power 2 is 1. Which means something happening once every year, once every 10 years, once every 100 years. The y-axis is the amount of rain in millimeters per day. 200 millimeters per day is, Cardiff probably all of it gets 800 millimeters per year. So 200 millimeters per day is like. The bottom graph in blue is what the climate says extreme 90th percentile rainfall is. Those are those plus signs. Okay? The ones that are in the green crosses are what observations tell us. Satellite observations. This is a CHIRP satellite. That's what data is. Notice the difference. Climate models don't produce extreme rainfall. Satellites are telling us one story, the climate model is telling us another story. This is today. So how can we overcome this gap? One idea that I told you before was, okay, climate model is 25 kilometers. Why don't we build a model at 5 kilometer resolution and run it? Because then at 5 kilometers you get very amplified rainfall, which can then resolve it else. Resolution is necessary to resolve. But this again, as I previously explained, it's too expensive a proposition. Enter machine learning. What you see here in the red stars, machine learning solution, and the lines that you see are basically extreme value distribution that will be fit to the data, and the shading are the contours. What we are able to do today, with just a little physics, I'll tell you what that means in a moment, and machine learning together, is to revolutionize the production of extreme events that are important to assess the hazard in the process of making decisions. Without these extreme rainfall events, we simply can't be designing systems that assess impact. We simply can't be using those systems for decision making. So while we can't produce the stack that I told you in the beginning of my talk, what has been really a bottleneck is how do we get to the details? And I will tell you that machine learning has made an enormous, even here, even though you would say, well, wait, isn't that machine learning dependent on data? Yes, it is, but you learn in a special way from model outputs that enable you to apply this vision. Okay, how do we do that? Okay, so I should stop so we can have a discussion. So let me just finish with how we have been able to do this and why it has been so impactful. At the left is the low resolution climate model, and the right is a high resolution output. The typical method is to take this low resolution climate model and then use it to run a very high resolution model. This is called detailed numeric. So you might have a special model over Mexico, which has a lot of resolution. You don't care about the globe, and that's the way it is. And this is called physical downside. And then you take a little bit of statistics after that post-correction, and you get high resolution. That's the traditional way of doing it, very, very expensive. The next way of doing it is just statistics. This is something you would all do. Grab a bunch of data, build a regression model, do something with it. and then call that the high resolution production, super resolution method. It doesn't work as well either, because the scales that we're talking are not like we do in photographs. The scales we're talking are going from like 50 kilometers to 5 kilometers each dimension. So that's 100 times. And so these are very large scale changes, so it doesn't really work. The third one is to use this reduced physics, meaning we say, we don't ask the machine learning system to figure out basic physics, like if something is conserved, or if this much rainfall fell and you have this big mountain, what would happen to the leeward side or the windward side? That's such basic physics that you shouldn't have to have the machine learning try to learn from it, which would require an enormous amount of data to learn this very elementary thing. So if you can provide it with very simple that are conserved, this is the linear response to rainfall that you expect under certain orography, or this is the kind of turbulence you might expect. It's very basic things, nothing detailed. Then you realize the machine learning starts to latch onto the right subspaces to be able to generate very good solutions. This was a revolutionary advance. It's published like a year and a half ago. And if you're interested, we can send you a lot more detail. And in this way, what we're doing is that we can now learn how to downscale the present time, apply to future time, so we can generate extraordinary resolution rainfall maps, extraordinary resolution flood maps, extraordinary resolution salinity maps. We talked about that. Extraordinary resolution heat stress maps. All of these things that are needed in the hazard layer to be able to drive exposure and vulnerability impact. So, in summary, I would say there's a few key revolutionary advances that have happened that are enabling us to think about climate in the future and sustainability. The first advance is actually the use of AI for vulnerability assessment. The second is the ability to do downscaling to very high resolution to simulate extremes in different climate environments. This is the second big advance that has happened. Third, I would say, is the deployment of very simple but gaming approaches such as serious games to engage community in a way that decision making locally is enabled, but also identifies gaps in how it can be scaled to ever larger scope. For example, all the way up to national adaptation plans. Many countries are. With that, I will stop and maybe we can discuss them. Thank you very much.
That might sound.
You can use the mic.
So do you have questions? Yeah, there are questions. Hello.
Thank you very much for your presentation. My question is, do you think that we really have the technology to conduct accurate risk analysis in Mexico? For example, here in Querétaro, recently we had a flood. It was not so big, but were some people that injured in this event of flood. How can we have this system here?
Okay, I'll give you the good news first. The good news is that here's how we would have a system. First, we're going to gather satellite observations over Querétaro, which they are very much available at very high resolution. Next, we're going to get climate models. can be run in present climate. And we're going to use this technology for downscaling to downscale with very high resolution and calibrate them against what the satellites would say. Then we'll run the climate model in future scenario, which could be 10 years from now, 20 years from now, 30 years from now. And we will downscale the outputs in each one of those. And we will produce a graph like this. For example, this is for rainfall, produce one for stress. We can produce one for other variables, all the variables. In fact, we're doing this in Bangkok, we're doing this in Bangladesh, in India. Every community wants to know what is my tail risk, what is happening in the extremes, because that is what informs my decision. To answer your questions, there is no hindrance to doing this in fact, it offers the perfect scale to be able to study this problem. And we can deliver a sub-kilometer scale over territory, which, how wide is it? 50 kilometers? 50 by 50? Great, you get a very detailed map. And what we have to now start thinking what happens beyond. What's happening to the water? What's happening to the ground cycle? How do we manage ground? How do we manage water supply? How do we have to first recharge? Then we recharge, and there's the groundwater supply. What's the total insulation? What's the total heat stress? All this has to be done. After you do that, you then have to go to the community and start working with them to see what issues they are facing and turn it into a decision problem that they can solve. But if insofar as the risk of hazard, the question you asked, the answer is very straightforward. There is absolutely zero problem. But for starting the work, there's money today to invest in a computer and 3 people who can dedicate themselves. In 6 months' time, we can do it. Absolutely, we can put these maps on a dashboard and say, here's what it looks like in present climate, here's 2030, 2040, 2050, 2060, and here's the uncertainty. And if you want to plan, tell me how risk-averse you want to be. We can do it, 100%. That's why I'm here, if you want to do it.
Morning, thank you very much. Excellent presentation. I think we enjoyed it. Congratulations. But there is something that I'm so worried about this. Because you already mentioned that, for instance, with these models and this perform using AI and some other machines like machine learning and so on. Wonderful. But at the end of the day, for instance, you also mentioned that this data can be used for someone in order to make a decision. Then, if we have this information, for instance, in the case of Bangladesh or Bangkok or whatever, but even so, if we can have it later on in Mexico, let's say, well, how this information will help someone, I don't know, in order to try to avoid or to decrease the effect of this climate change, because climate change is a real fact. We are suffering. But so somebody said also that we are late for presenting some solutions, or presenting something in order to avoid this. Somebody said, no, it's because we are quite late. So this complicated, it's a quite complex problem. I mean, I'd like to know which would be your idea or your proposal for saying, okay, guys, we have this, and we are now here in 2025, and perhaps picture in 2050. But what we can do in general as a human being, because otherwise we are in this situation, all of us will suffer this. So what we can do to avoid it, right?
So your question itself is really complex.
Yes, sorry, please. I'd like to hear your experiences. So
There are ways of thinking about the problem at different scales. Countries, for example, think in terms of national adaptation. So what do you need for a national adaptation? You want to know the wind hazard. here is what the wind speeds will be. Extreme wind speeds are likely to be. Here's a 100-year wind speed. Here's a 100 years wind speed. We want this information. So national adaptation can be done. What does national adaptation mean? Where do I build shelters? Where should I build new structures? What should be my design specification for roofs? How should we be? These are all happening in the national. And it's not just wind, it's flood. The national flood hazard. The national heat stress map of Mexico. What's the heat stress drought map of Mexico? We're not talking about this in present time, which presumably can derive from this. We're talking about projections along with the uncertainties in future climates that we could experience and use that information. I haven't told you how, but use that information to start planning a transition, an adaptation transition. Why are we talking about adaptation? Why can't we just go put a bunch of towers and carbon out of the atmosphere? We're done with it. It's not going to happen. There isn't a technology today that will save us. We have mitigation will not get us through. Therefore, adaptation needs to happen. We have to adapt. People have to move to cooler places. People have to move away from where there are floods. People have to engineer their systems to that. And this can happen, as I mentioned, at different scales. Scale number one is the national scale. By the way, he's building a national adaptation plan. There's a national adaptation plan for Thailand. Adaptation plan for Bangladesh. There's a national adaptation plan for India. Imagine actually Mexico is also building a national adaptation. This is the government thinking. Here comes what I heard in your question. It is completely devoid and disconnected from what people expect. These are very grand plans. Or we'll double our forest. The people on the ground, they don't care about this. They want to know what will happen to their crop calendar. What should I plant in the next season? And they want to understand why is climate important. Their experience of climate is that they get flat left and right every year. Their experience of climate is not what's going to happen 50 years. They could care less. But what is important for them to realize is that unless they transition from this fatalistic short-term thinking to risk-based thinking, maybe not 50 years, but at least 10 years, they are able to put even their meager resources together in a way that can help them adapt that. This is the change in thinking that a person must have educationally in transitioning to climate. How this happens requires a lot of people, a lot of educated scientists going out there, a lot of educated social scientists, a lot of educated high school students, all of them. And it requires a program, for sure. But let me take the example I have. This is why we like the approach we do. We didn't go there telling them a solution. You know, nice guy has from America telling people in Bangladesh what to do. As this has happened throughout the region. That's how they got the boulders. The Dutch came and said, we know how to solve that problem. But Americans solved it. India didn't do it. It doesn't have this problem. Like Bangladesh. So what do we do in this situation? What are we trying to do? We go and we start backwards, not forward. It comes and gives you climate map. What are the people's approach? How do you do it? How did you do it in the past? What are your influences? We encode this knowledge in those graphs that I talked about. Just computational machinery events. But the outcome are assessments that we have conversations with them about. And they then decide what action to take. They feel empowered. For example, in one village, everybody came together and made a common insurance pool. This, of course, won't save them from the big cycle. But all the little issues, they now have a way of handling. They went and had a conversation with the microcredit people so that they can build houses that can also serve as shelters. So there are solutions that indicate continuous adaptation within your means, in your place. That can then scale to bigger ones because others want to help. see that there is a pathway with an injection of capital or an injection of something, you can enhance the solution. So that's sustainable decision making is local. The global ones are more towards mitigation. They never seem to reach the people. I have not seen a single adaptation plan make impact. But there are ways for us to reach people, improve their understanding, enable their decision making, and identify gaps for the connection top down and bottom up can be made. I'm hopeful actually, not as pessimistic as you might be.
Unfortunately, I think that we ran out of time. The good news is that we are going to have a workshop with Sai. It lasts 4 hours, and I think that there will be plenty of time to answer your questions. Sorry, but thank you very much. Okay. Sai, thank you very much. ICASAT conference. You're present.
Okay, thank you.
Thank you very much. Announcement from the
Hola, hola, buenos días. Por aquí tenemos gente que va a estar con nosotros en workshops. Son en Gómez Morín, si quieren vamos pasando para allá, en el acceso A. Entonces ya están ahí distribuidas las salas, tienen una señalética para que vean cuál les toca. Bueno, si hay alguien que le faltó o tiene dudas, pues puede venir con nosotros. Estos son los workshops que estuvimos ofertando en la página. Entonces por ahí nos vemos. acompañarnos. Bueno, les comentaba, el día de hoy vamos a continuar con la última sesión de ponencias técnicas y posteriormente a las 4 vamos a tener la última conferencia magistral y después la ronda de premiaciones y cierre. ¿Okay? Entonces, bueno, vamos a iniciar esta sesión con la presentación, bueno, con la ponencia de Martín Moreno. Su trabajo es Experimental Validation of the Geometric Qualification to the Sabonius Rotor for Cell Starter. Adelante, doctor. Cedo la palabra.
Sí, bueno, sí. Bueno, lo que vamos a presentar es reacción experimental de una turbina vertical. Entonces, ¿por qué hacer una turbina vertical? Ustedes han visto en Querétaro, en la parte de Huimilpan, hay turbinas horizontales. Las turbinas son de un tamaño considerable. Sin embargo, hay una forma de aprovechar el viento, un ambiente urbano, es a través de turbinas verticales. Las turbinas verticales, a diferencia de las horizontales, utilizan el viento turbulento para aprovechar la energía del viento y así girar. Entonces, del lado derecho de ustedes, van a ver una geometría clásica de una turbina vertical tipo Sabonius, en la cual esta no tiene autoarranque o arranque propio. ¿A qué hacemos referencia con eso? La única forma de poder arrancar una turbina de este tipo es de forma pasiva o activa. La forma pasiva es a través de cambiar la geometría de las palas o la configuración geométrica o añadirle algo extra a esta turbina para que pueda arrancar. La otra forma es meter un generador o un motor eléctrico o una máquina eléctrica, inyecta uno energía a través de una modulación PWM y metes toda la energía reactiva para que el motor empiece a girar y así gira la turbina. Una vez que está girando, desenergizas y cambias la configuración, pues el rectificador, el inversor trifásico o bifásico, cambia su control y empieza a rectificar para generar electricidad. Esa forma de hacerlo eléctricamente es compleja, entonces una de las formas para esa solución es cambiar la geometría. Entonces, en este artículo justamente fue lo que hicimos, cambiamos la geometría, aprovechamos que el mismo viento nos empieza a empujar, pero lo más complicado de un autoarranque es que a velocidades de viento bajas, podemos llamarlas bajas de 1 o 2 metros sobre segundo, pueda la turbina por sí sola girar. ¿Por qué? Porque la inercia del motor se conecta con el generador o también la misma masa de la turbina le complica su rotación. Entonces, esta turbina clásica generalmente tiene un coeficiente de potencia o la relación de potencia-viento de 0.2. Entonces, tiene un autoarranque súper pobre porque puede arrancar hasta los 3 o 4 metros sobre segundo. Tener unos canales de viento de esa velocidad es muy complicado. En unos entornos urbanos, por ejemplo si se fijan aquí en la salida, hay que tener un canal de viento que más o menos ha de estar como entre 2, 3. Entonces, una turbina como de este tipo no podría girar en un entorno urbano. Entonces, justamente es la motivación o el problema. O sea, ¿qué podemos hacer del cambio de la geometría para que pueda generar esa rotación, ¿no? Entonces, dentro de toda la gama de las configuraciones o de las modificaciones que se puede hacer en la turbina vertical, escogimos añadir 2 turbinas y desfasarlas con un ángulo en particular. Primero pusimos en nuestro problema, ¿qué pasaría si el ángulo de la pala no sea totalmente recto, sino una desviación intermedia, aquí hacemos referencia intermedia, que la mayoría de los artículos lo ponen un ángulo de pala de 45 grados, sin alguna justificación. Sin embargo, en otros artículos mencionan que 12.5 puede ser una modificación mínima que puede apoyar en la velocidad de rotación. Entonces, escogimos una pala totalmente baja en inclinación. También añadimos tres palas, bueno, 2 y 3, 4 palas. Hay una diferencia entre cada una de ellas, tiene unas ventajas y desventajas. 2 palas generas una rotación con torque constante. 3 palas puedes tener una rotación constante. Sin embargo, generas mayor resistencia al aire y eso puede provocar que gire más lento. 4 palas giran, pero estás generando una mayor restricción para que el motor gire, o la turbina gire. Entonces, ya conociendo que el ángulo de desfase es de 25 grados y tenemos una limitante porque esta configuración va a ser distinta a las que ya existen, entonces la fabricación tiene que ser a través de una manufactura aditiva, pues empezamos a trabajar varios puntos. Ya tenemos 25 grados. ¿Qué tanto debe ser el desfase con respecto a? Hicimos una optimización de todo el rango completo de desfase y encontramos donde les enmarco un color rojito de 55 a 75 grados de desfase. Tenemos puntos interesantes. Escogimos en este caso 65 grados, ya que todas las curvas de viento nos dan el coeficiente de torque o la resistencia al aire muy similar. Entonces preferimos seleccionar donde podría ser lineal los valores del coeficiente a otros valores que nos pudieran cambiar la dinámica en estado estacionario de la turbina. Entonces aquí te los muestro, ¿no? Si se fijan, en la pala tenemos 25 grados y el desfase entre ellas son 65 grados. Entonces hicimos cambios mínimos en la geometría que nos mejoró bastante porque la que les mostré al inicio, esa arranca entre 3.5 a 4 metros sobre segundo y esta arranca sola en 2.3 metros sobre segundo. Entonces en canales de viento bajos puede arrancar bastante bien. Entonces, nosotros para poder hacer esta optimización usamos unas ecuaciones de Navier-Stokes que son simuladas y resueltas en el ANSYS. Y a la par, después de los resultados, tenemos los coeficientes de potencia, que es la potencia del rotor entre la potencia del viento, y el coeficiente de tanto se determina el en Nancy nosotros hacemos un dominio computacional en donde colocamos la turbina y tiene que tener cierto tamaño de acuerdo al diámetro de esta turbina. En nuestro caso, nuestra turbina es de 10 centímetros de diámetro. Entonces, si se fijan, por ejemplo, es 10D o 5D, eso son el diámetro multiplicado por la distancia que está ahí. Eso nos ayuda a encontrar espacio donde va a estar o donde se va a solucionar las ecuaciones de la Navier-Stokes. Al mismo tiempo, mientras vamos acercándonos a la turbina, vamos haciendo un mallado más pequeño para terminar la malla y la solución realmente sea óptima y que se ocupe en la menor cantidad de recursos computacionales. Entonces, hacemos diferentes mallados y escogemos el mallado que computacionalmente nos genera menores recursos, porque la computadora puede tardar 1 o 2 días en dar solución. Entonces, estamos siempre buscando la optimización para que esa solución sea lo más rápido posible y cercano a los valores. Entonces, en el laboratorio de la universidad empezamos desde hace 3 años a hacer un túnel de viento con los estudiantes. Este túnel de viento es a mano. La ventaja, a diferencia de otros túneles de viento que tengan otras universidades, es que nosotros tenemos la tecnología desde cero. Entonces, el control de viento, los parámetros del viento están totalmente controlados por nosotros y nosotros conocemos exactamente qué está pasando dentro de él. Esto nos permite que la validación experimental sea muy cercana o cercana a la solución computacional. En este caso, si se fijan bien, tenemos un sistema de potencia, tiene tres, aquí no se ven, pero tiene tres motores brushless, están manejados de forma eléctrica a través de un inversor trifásico. Este inversor trifásico tiene una modulación tipo senoidal, la cual optimiza el switcheo y inventa una potencia reactiva para que empiece a tirar los motores brushless. Tenemos, aquí no lo ponemos justamente porque es industrial, nosotros tenemos unos ventiladores especiales con cierta configuración que implica la mayor cantidad de viento con la menor resistencia al aire para que podamos golpear bien la turbina y controlar el viento. Si se fijan bien, el tipo de túnel de viento es una configuración cerrada. ¿Qué quiere decir eso? Empujamos viento y el mismo viento que está golpeando la turbina se regresa y el mismo lo vamos empujando. Si lo tuviéramos en el lazo abierto, quiere decir eso que no sensáramos cómo está el viento de entrada, el viento de salida, nosotros no pudiéramos definir y controlar los set points de viento para que esta turbina validar de forma experimental y conocer los errores que tenemos de forma real. Entonces nosotros lo controlamos a través de un control clásico de PID. Sin embargo, la función de transferencia del túnel de viento es de primer orden, pero cambian los parámetros de la función de transferencia con la temperatura y con la turbina. Si yo pongo una turbina nueva totalmente distinta, las constantes de ADKI son totalmente distintas, entonces nuestro control lo que hace es sintoniza de forma automática y le pone los valores de las constantes a setea para que estas lleguen a los valores del set point que nosotros estamos buscando para que la prueba sea replicante y tenga reproducibilidad. Entonces, una vez que encontramos, bueno, que ya les mostré cómo hacemos la validación experimental, nos pasamos a poner la turbina dentro del túnel y calculamos los coeficientes de potencia y los coeficientes de torque. Si se fijan bien, nosotros aproximadamente en 3.4 de lambda, que es la ganancia entre el viento, la velocidad del viento y la velocidad de rotor, tenemos un coeficiente de potencia de 0.35, que si se acuerdan del principio, nosotros teníamos 0.2. Entonces, ganamos, somos superiores con respecto a la turbina clásica. Aparte de que podemos girar a menores velocidades de viento, podemos producir eléctricamente o podemos producir la mayor potencia que una turbina convencional. Esto es lo que quiere decir. Entonces, fíjense bien, aquí les voy a mostrar un video en el cual se muestra el autoarranque aproximadamente a 2.3 metros sobre segundo, que es la velocidad en la que arranca. Ahí está nuestra célula, se está arrancando y se mira de forma automática, arranca y se empieza a acelerar hasta que en estado estacionario se queda a una velocidad de rotación constante. Entonces, justamente es lo que se demuestra ahí. Aquí nuestra interfaz no es tan bonita todavía, por eso no coloqué como poníamos nuestros endpoints. Sin embargo, a bajas velocidades, nuestro rotor gira a una buena velocidad. Este artículo ya lo hemos publicado de forma simulación, aquí lo publicamos de forma experimental. Y en comparación con varios de los artículos que hemos encontrado, tenemos un autoarranque mucho menor. Y es comparable con muchos artículos del estado del arte. Entonces, ¿para qué generar turbinas de tamaño pequeñas? Por ejemplo, eso sí me pasó. Decirles que nuestras turbinas son de tamaño micro. a escala micro, conforme a lo que hemos realizado en la literatura, la hemos seteado o la hemos definido, que van desde 10 centímetros hasta 1,5 metros de alto. Después de ahí siguen otras escalas, nosotros en nuestra escala, conforme a lo que tenemos en el laboratorio que hemos construido, pues, hemos desarrollado turbinas de tamaño micro. Actualmente, por ejemplo, ya hemos conectado nuestras turbinas con un generador eléctrico para obtener las potencias que se pueden obtener a través de un entorno urbano real. Porque aquí en la turbina tenemos entornos de viento controlados. Nosotros podemos, por ejemplo, poner una rampa de viento que empiece de 0 a 2 metros sobre segundo con cierta pendiente para que puedan arrancar. Sin embargo, en los entornos urbanos pues puede pasar nave o puede pasar demasiado sol y el coeficiente del viento se nos modifique y ya no pueda girar. Entonces necesitamos conocer exactamente, por ejemplo, que llovió, ¿no? La lluvia nos hace que no capturemos electricidad porque como está totalmente húmedo y está totalmente lloviendo, las turbinas no se mueven por nada. Estamos viendo que lo esté golpeando todo el tiempo para generar. Una de las ventajas que a futuro es que se puede combinar la generación eléctrica del viento con la generación solar. Ese tipo de generación híbrida pues, puede apoyar para diferentes aplicaciones. Bueno, en conclusión, la turbina que generamos tiene un desfase de 75 grados, con una desviación de la pala de 25 grados, tres de ellas, pues es superior a las turbinas clásicas y algunas de las que están reportadas. Aquí demostramos, y con parte del video, de hecho el video también lo tenemos en YouTube, en el canal de nuestro laboratorio, donde mostramos cómo a bajas velocidades sí se puede arrancar la turbina. Entonces, esto se puede utilizar a futuro para redes inteligentes descentralizadas. ¿Qué quiere decir esto? Que yo no necesito estar conectado a la red SP, sino puedo generar electricidad y desde ahí alimentar cargas eléctricas lineales o no lineales, dependiendo de lo que ocupe, hacia cualquier uso doméstico urbano que se intente realizar. Entonces, a futuro, si se fijan bien, podemos aumentar la escala y estamos ahorita trabajando en irnos a la escala media, a la escala baja, a la pequeña, que son turbinas superiores a 2 metros. Entonces, ahorita es lo que estamos trabajando, sin embargo, aquí les muestro los primeros resultados que tuvimos de. Gracias.
Abrir sesión de preguntas. Espacio para par de preguntas. Yo voy a empezar con una. Me llama la atención que dice, bueno, puntos dijo que estaban protegiendo, que no podía dar toda la información porque esta parte de ahí ¿cómo están haciendo este proceso? O sea, ¿qué van a proteger y cómo va a ser el proceso de?
En el caso de la pala, no hemos querido ni publicarla ni hacer patentamientos de parte del laboratorio. Sin embargo, actualmente estamos trabajando en la redacción y en la validación de la sincronización, de la autosincronización del control PID a través de los parámetros que se obtienen de la probeta. La probeta me hago referencia al motor. Eso sí lo estamos trabajando y vamos a publicarlo, pero el siguiente año. Sin embargo, la otra parte consideramos del equipo de laboratorio que no deberíamos hacer.
Gracias.
Hola, muchas gracias. Me parece muy interesante la aplicación. Algunas de las principales desventajas de otras turbinas eólicas, pues es que pueden tener impacto en la fauna. Además de que hacen mucho ruido, o sea, tienen muchas implicaciones medioambientales. ¿Usted Analizando esto, planeación a futuro, analizar estas ventajas y ponerle pues números.
Sí, hemos encontrado que empezamos con las micro. Estas microturbinas generan bajo contenido de ruido auditivo para las personas. Entonces, lo que queremos demostrar, lo que hemos determinado es que la cantidad de turbinas en proporción de volumen para una grande puede generar la cantidad eléctrica igual, casi igual, pero sin la menor cantidad de ruido. La ventaja de estas es de que una vez que te golpea el aire, el viento se vuelve laminar y solamente es turbulento 3 veces el tamaño del diámetro de la turbina. Entonces, por ejemplo, si estamos hablando de 10 centímetros, a los 30 y después se vuelve otra vez laminar. Entonces, no afectamos la fauna y afectamos a las personas porque muchos artículos mencionan que tener una turbina vertical cerca de su parte urbana puede generar dolores de cabeza. Se ha descubierto eso y también problemas auditivos. Estas turbinas de tipo micro, que son tan pequeñas y también no molestan, no generan ruido visual, la geometría o la arquitectura. También tiene esa ventaja.
Muchas gracias, doctor Martín, por su presentación. No me quedó claro esta turbina en particular, cuál era la.
La capacidad se demuestra a través del coeficiente de potencia, que hace referencia a la relación de la potencia del rotor a la potencia del viento. Entonces, la potencia que puede generar es 0.33, 0.34. Esa es como es un coeficiente, no tiene magnitud. Sin embargo, cambia cuando se conecte un generador eléctrico, la inercia del generador eléctrico va a meter una restricción extra, aparte de la mecánico mecánico. Entonces, seguramente, ya no baja el coeficiente de una prestación eléctrica inferior a la potencia mecánica obtenida a través de los experimentos. Sin embargo, lo que se hace ahí es encontrar un mecanismo que aumente la velocidad o el torque, dependiendo de lo que queramos, para la parte eléctrica. Si queremos velocidad, si queremos contacto, metemos la velocidad, si queremos corriente, metemos el torque. Y de ahí lo metemos a un inversor que puede trabajar dependiendo de la máquina eléctrica y de ahí mandarlo a un bus DC o dependiendo mucho del tipo de carga, la carga es AC, la carga es DC, y las cargas eléctricas que se van a poner son lineales, productivas, capacitivas, o son no lineales, que sean algún inversor, algún rectificador, algún sistema que esté switchando y que genere bastante ruido eléctrico en la red. Esto también se tendría que usar. Generalmente se usan motores axiales, que esos motores axiales generan mayor cantidad de torque, para la red de forma de
Muchísimas gracias, doctor Martín. De parte de tenemos un pequeño souvenir. Y bueno, un aplauso.
A continuación, tenemos a nuestro compañero Alfredo Puente, quien nos hablará sobre Parametric Storing and Benchmarking of Surrounding Dripper for Orbital Grasping. Un aplauso para él, por favor.
bueno, lo voy a tratar de hacer un poquito la introducción algo rápido, ya que ayer el doctor Sayano nos hizo el favor de introducir un poquito qué pasa que hay en órbita de basura espacial. Y bueno, en órbita ya sabemos que hay basura espacial, pero las estrategias más utilizadas ahorita y más que puedes encontrar en los diferentes artículos es tener redes o arpones. Sin embargo, obviamente va a generar a la larga. Las redes no las pueden utilizar, solo las pueden utilizar una vez. Entonces, como solo las pueden utilizar una vez, tener ahí pues una pérdida, vas a tener otra vez más espacial. Y los arpones pues generan partículas al momento de atravesar. También tenemos otro tipo de tecnologías que han sido propuestas, que Letter Breakers, Robotic Arms, letters electrodinámicas, láseres, polímeros, bueno, este es conceptual, todavía no ha sido más cierto. En base a polímeros, hacer una especie de foam que pudiera ahí entorpecer un poco, reducir la velocidad y generar que se pudiera más fácil esa basura. Dentro de otras estrategias que hay, pueden tener satélites modulares o SEOs, que es como si fuera una especie de paracaídas que le hace una especie de drag al satélite, pues lo va a frenar. Sin embargo, como podemos ver, hay una necesidad y está creciendo de capturar basura espacial. ¿Por qué? Porque hay más de entre 1 y 10 centímetros según la Agencia Espacial Europea. Entre 1 y 10 centímetros podemos encontrar estimados en el 2024-2025 1.2 millones de partículas entre 1 y 10 centímetros. Entonces, la forma más fácil de atraparlos podría ser usando brazos robóticos, grippers, de tal forma que los puedan reutilizar y no sigan siendo basura. Y además, puedes tener satélites que sean modulares y cambiarles piezas y esto en un entorno de ser friendly del espacio. Como ya sabemos, los grippers pues tienen sus problemas también, los que son, vamos a llamarlos rígidos, porque los diseñan, pero solo se pueden adaptar a cierto tipo de objetos, y en este caso vamos a tener objetos que van a estar tumbling, o sea, van a estar moviéndose en el espacio, y esto va a ser muy rápido. La forma más fácil de hacerlo es tener algo que se adapte. El tener algo que se adapte, nosotros estamos proponiendo tener robótica suave, algo de soft grippers. Entonces, dentro de las ventajas que tenemos es que tienes ICASAT compliance para tener un contacto más seguro. Tienes adaptabilidad para, no solo para se me fue la palabra, de diferentes tipos, sino para ambientes que no son estructurados. Y también tienes, pues obviamente, los clippers han demostrado tener algo de damping para los objetos al momento de capturarlos. Tenemos una variedad muy grande de stop creepers que han sido propuestos, que podemos encontrar en la literatura, pero la mayoría de ellos no se pudieran adaptar fácilmente al espacio, que tienen muchas piezas, pues están fluidos o requieren algún cambio en la temperatura. Entonces, hay que proponer algo que pueda funcionar en el espacio. Nosotros estamos proponiendo en este caso un diseño de los dedos en el que tenemos compliance, compresibilidad y capacidad de damping. En este caso tenemos este tipo de diseño que incluye falanges, y dentro de los falanges tenemos un material celular, una metaestructura. En este caso que vamos a presentar aquí es como una metaestructura. Estamos usando una geometría que se puede encontrar en metamateriales, que es una honeycomb hexagonal
reinforcement, que es esta en este caso. Y que tenemos también, que nosotros estamos proponiendo que sea tendon driven, lo cual nos quita de tener actuadores que no son prohibitivos para el espacio. Y tenemos part count reduction, reducimos el número de partes, porque eso simplemente es monolítico en este caso. Anteriormente hemos hecho una publicación en la que habíamos presentado este modelo que utiliza 6 motores y tiene cada dedo 2 tendones, uno que es para la compresión y otro que es para generar ahí la parte de bend para poder adaptarse al movimiento. La compresión lo que nos da es que tenemos una variabilidad en el stiffness de los dedos y eso nos da que podemos tener todavía más configuraciones de fuerza al momento de manipular objetos y nos da un agarre. Sin embargo, bueno, para este modelo que estamos usando, debemos usar un manipulador pequeño, decidimos utilizarlo. Completamente se quedan igual las geometrías, son escalables. La fuerza que medimos para este modelito es de entre 1.8 y 2.9 newton. Y bueno, aquí tienen el diseño. Vamos a tener diferentes ¿cómo decirlo? Supuestos que vamos a hacer para trabajar con esto. En este caso estamos proponiendo un supuesto de un CubeSat. Un CubeSat mide por lado de su cubo de 10 por 10 por 10. Entonces estamos usando ecuaciones de impulso y para el caso simétrico que tenemos, elaboramos ahí esta representación donde tenemos como frontera 2 newton por dedo en la actuación y encontramos que podemos ahí las velocidades angulares del objeto que puede estar rotando y cuánto tiempo más o menos tendríamos de captura y cuánto la región azul sería todo lo que es posible y lo que no, ahí podemos tener la línea magenta que es la barrera de lo posible y no lo posible para un modelo como el que estamos teniendo en este caso teniendo estos supuestos, ¿no? ¿Qué es lo que tenemos aquí? Que es todo por tendones, es completamente escalable, se puede escalar, incluso se puede cambiar de material, estamos usando TPU, esto debido a su elasticidad, pero para el espacio obviamente el TPU pues, no funciona, se pueden usar otro tipo de materiales, se puede poner en titanio, por ahí hay diferentes artículos del profesor Howell que trabaja Compliant Mechanisms y habla de mecanismos compliant para el espacio comunitario. Ahorita recientemente incluso sacó un filamento de impresión 3D que se puede usar para el espacio. Sería cuestión de probar y adaptar estas particularidades. Tenemos reducción del número de partes, la masa obviamente se reduce considerablemente en comparación con los modelos anteriores y tenemos damping pasivo de los fingers. Una cosa en la que hay que tener mucho cuidado con los soft riggers es que siempre van a tener deformaciones fuera del plano. Y estas deformaciones que son fuera del plano lo que te van a dar son inestabilidades al momento de que tú quieres agarrar una mata. Entonces, para tratar de bajar un poquito esas deformaciones que tenemos fuera del plano, estamos proponiendo aumentar el thickness de los team members que están ahí de la geometría y tener desde 0.9 hasta 1.5 milímetros, hasta 1.7, perdón, y después tener combinaciones que puedan reducir la deformación. En este caso ahí tenemos las gráficas y vemos que si nos quedamos entre 0.9 y 1.3, la mejor opción de estabilidad que tendríamos sería usar fines de 1.3 para darle a los dedos un poco más de estabilidad en el agarre. Otra cosa que también estamos explorando con estos dedos es que podemos tener stiffness, pero que sea de una forma graduada de toda la distancia de los dedos. Entonces nos estamos ocupando. Por ahí habíamos hecho un estudio anteriormente de qué geometrías se pudieran ocupar, pusimos diferentes geometrías y experimentalmente y por simulaciones calculamos el módulo de ion aparente para cada una de las geometrías. Y en este caso estamos proponiendo tener una combinación de geometrías que cambia un poquito las dimensiones. Y esto lo hace cambiar el módulo de ion aparente. Por aquí tenemos unos clusters hechos por K-means del original, que está a la izquierda, y en la derecha podemos ver el que tenemos graduado, que cambia la media de los desplazamientos, y pues eso nos dice que efectivamente se puede ser graduado. Claro que hay que hacer mayores comprobaciones, pero por distancia es bueno. Vamos a poner aquí vamos a representar, hicimos diferentes experimentos donde era un objeto, un contenedor de 2.3 kilogramos. Teníamos una free floating, experimentos en free floating, también tenemos donde suspendemos el objeto y está girando y lo tomamos y reducimos ese movimiento que tiene. La fricción en las fingertips que tenemos ahí está, lo que medimos y el límite que teníamos. Este es el primer experimento. Este es free floating, que tenemos una mesa con frictionless stable, en la que tenemos unos bearings que hacen que tenga menos fricción. Tenemos dos casos: el que tenemos del handle, le llamamos Space Kettle, Space China, y de un conector. En el siguiente experimento tenemos el mismo contenedor, esta vez suspendido. Le dábamos una velocidad inicial, movimiento, y teníamos lo mismo, tratar de capturar el handle y el conector. Aquí hay unos videos que no sé si primero aquí podemos ver, bueno, va un poquito lento, pero trato de tomar el handle del kettle y después lo va a mover para demostrar que efectivamente lo tomó. Los dos casos. Y en el otro iniciamos con un movimiento, va a detener el movimiento del objeto y a capturar lo mismo en el siguiente. En conclusión, bueno, diseñamos un Reaper que puede ser utilizable para captura de basura espacial y también para servicios de satélites en el espacio. El Reaper tiene no hace ningún disturbance en el objeto que sea considerable. Teóricamente, bajo las instrucciones que utilizamos, los supuestos, perdón, teníamos que puede tener un CubeSat. En este modelo reducimos la complejidad mecánica que teníamos respecto al primero. Obviamente que el trabajo futuro queda buscar alternativas de materiales y probar el endurance que puede lograr tener, ya que en todos los mecanismos compliant, en todos los soft flippers, los soft fingers, vamos a tener que, mientras que nos movamos en la parte elástica, vamos a seguir teniendo el mismo comportamiento. Pero si nos movemos en la parte plástica, ya no va a regresar a donde está. Y eso pues, nos da problemas. Sería todo por mi parte. Muchas gracias. Y si alguien tiene alguna pregunta, bienvenida. Gracias por venir con nosotros.
¿Alguna pregunta? Hola, buenas tardes. Tengo una pregunta. Una vez que tengan diseñado el prototipo, ¿cómo van a llevarlo al espacio?
Bueno, se llevaría en un satélite. Obviamente hay que tener ahí en cuenta que hay que hacer experimentos de vibración para saber qué es el mecanismo. Y después se llevan los satélites simplemente y se suelta igual que los demás satélites.
¿Y de durabilidad cuánto tiempo tendría?
Dependería del, como dije, en esta iteración solamente estamos usando TPU. Entonces, TPU obviamente no es graduado para el espacio, necesitamos buscar los materiales, en este caso podría ser titanio, o este nuevo filamento que está poniendo, cada día salen cosas nuevas, podemos usar compósitos. Bueno, sería probar realmente la estabilidad y las fuerzas que vamos a tener y cuánto se va a mover el mecanismo interno. Va a variar el material y el todo necesita.
¿Alguien más?
Muchas gracias. El diseño del dedo incluso parece dar idea de que puede imprimirse.
Sí, precisamente la compresión lo que habilita es tener variabilidad en el estilo. Queremos agarrar un ejemplo, si solo dejamos con el bending, vamos a tener poca fuerza en la inflación. Vamos a tener un agarre inestable, vamos a llamarlo así. Es lo que muchos critican de los softwares de robótica suave. Pero si le damos variabilidad, hay varios casos en los que se puede hablar de variabilidad, puede ser con tener dos tipos de actuaciones al mismo tiempo, puede ser botón y neumática, en este caso la disponibilidad para el espacio, pero en este caso la compresión lo que hace es que reduce el largo del dedo, el largo del dedo, más fácil depende y cambia y tenemos más.
Una pregunta de seguimiento, ya que mencionaste, tenemos una colega que trabaja en robótica y ella siempre usa mantra. Entonces, me resultó curioso que mencionaste que es prohibida en el espacio.
Es difícil llevar fluidos al espacio. Es difícil llevar fluidos al espacio. Es mejor hacer otro tipo de mecanismo o actuación que sea más fácil de llevar que llevar a fluidos. Una es si llevamos fluidos, hay diferentes temperaturas, hay cambios de temperaturas extremas, tienen radiación, otras cosas, entonces afecta el mecanismo. Incluso los mecanismos normales se afectan debido a los cambios y todo esto. Por eso es que también para hacer la variabilidad en sistemas hay artículos en los que se sugiere, por ejemplo, agregar materiales termodeformables en el espacio. No es una opción. Para robótica suave, aquí lo mejor de actuación, donde vamos a tener las fuerzas más grandes de capturar un objeto, va a ser obviamente con fluidos neumáticos. Es lo ideal.
No, hay otra etapa que siento yo que hace falta en esta solución y es el sistema de aplicación de los objetos.
Sí, eso estaría bien.
¿Quiénes están?
Por ahorita estamos en la parte pero sí hay que tener un mapeo de cómo se está haciendo. Por ahí había una compañera de la maestría que trabajaba un poquito en identificar objetos en el espacio con la emisión. Gracias.
¿Tenemos espacio para alguna otra pregunta? La Bárbara.
Tengo una duda porque comentas que sea reutilizable, pero me gustaría que abordaras un poco más en qué es reutilizable, o sea, cuántas veces o qué define que sea reutilizable.
Okay. Por ejemplo, si usamos Japón, la Japón solamente tiene una carga, lo voy a lanzar al satélite, va a golpear y listo. Ahí quedó, ya no se puede reutilizar. Lo podríamos tratar de regresar, es difícil. Las redes la voy a aventar y agarro el objeto, bien. Si hizo el handling en el objeto, bien, lo podemos arrastrar. Pero si no, ya perdí la red, ya perdí la carga, adiós. Entonces, el momento de utilizar robótica, un brazo, un grip, lo que sea, para arrestar el objeto, pues obviamente podemos tener más veces que podemos intentar atrapar. Solamente un solo tiro y arriesgarnos a eso. Y del otro lado es que se están proponiendo satélites que sean modulares. Tener satélites modulares, puedo cambiarle piezas y hacer un purposing del satélite. Esa es la parte que es reutilizable. Y reutilizable en el Reaper sería que lo puedes utilizar varias veces para tratar de hacer una captura en el espacio.
Bueno, estamos ya agotando el tiempo. Si hubiera más preguntas, le agradecemos a Alfredo y nos tenemos un pequeño sumerio de
Muchas gracias.
Bueno, estamos llegando al final del congreso. Todavía nos falta cerrar con la última ponencia. A las 4 de la tarde nos vamos a pasar a la zona de gameplay. Por ahí hoy se tiene que acabar. Entonces, bueno, los invitamos y nos vemos aquí unos minutitos antes de las 4, por favor. Sigue la presentación del doctor. Él viene del Reino Unido y posteriormente pues la sesión de premiaciones y clausura. Entonces, unos 5 minutos antes de las 4, por favor.
Today, the third day of the International Conference on Applied Science and Advanced Technology, it is both an honor and a privilege for me to introduce a distinguished guest of understanding this program, Professor Monjur Mourshed. Mourshed is an internationally recognized academic known for his leadership in sustainability and climate change. He is currently Dean of Environmental Sustainability of Sustainable Engineering at Cardiff University, UK, where he leads the integration of climate teaching and community engagement. His curriculum in architecture, engineering, and digital technologies, applied to the development of smart, resilient, and low-carbon cities. His line of research focuses on smart and resilient urban environments, the energy design and operation of buildings, and change adaptation. His work reached academic research with practice and policy making, contributing to the development of communities worldwide. It with great pride and gratitude to invite you to warmly welcome Professor Mourshed.
Thank you. Thank you all for coming today. Very nice introduction. So I'm going to, I know we are a bit delayed, so hopefully I will finish my presentation in time. So I'm going to talk about how we have moved from predominantly physics-based simulation towards AI-driven digital twins, not just for individual buildings, but for cities and countries. And I will kind of talk about past 20 years of research in this area and try and explain why we did what we did. So before, sorry, okay. So before moving on to the presentation, I'm not sure whether all of you know about Cardiff. Cardiff is the capital of Wales, one of 4 countries in the UK. So you have the Scotland, that's the part, England, the red part. Cardiff is the green small part in there. And you also have Northern Ireland. One unique thing about Wales is that people in Wales are very passionate about sustainability. And we like to say that we are leading for 2050 net zero transition. And Wales is the first country to legislate the interest of future generations. Everything Wales does, they have to test the policies that is fit for purpose, not just for today, but also for future generations. That was legislated back in 2015, so 10 years ago. It's a bilingual country. Another interesting fact about Wales is that the symbol, national symbol, is red dragon. So we are better than Scotland. That symbol is unicorn. So dragon is better than unicorn. And Cardiff University is a very large university with 30,000 students in 3,000. In the UK, it's called the Russell Group University, which is something similar to Ivy League in America, States. We have 2 Nobel Prize winners and a couple of fellows of Royal Society. And this is what Cardiff looks like. It used to be a port city, and during the time of the Sugar Revolution, they used to ship coal from Cardiff to all over the world. So you could say that climate problem, it was because of Industrial Revolution, it is because of coal. So Cardiff contributed to the problem, we are trying to contribute to the solution. So before moving on to the methodology or the transition from simulation to AI, let's take a look at what is the challenge for sustainability. So I know it's very simplistic, but bigger challenge for sustainability today is global net zero targets. That we want to reduce our emissions to zero. When we reach that, that's a question for every country individually. That's where we want to get to. And so that net zero target is staged through carbon budgets. So we will reduce 5% this year, 10% next year, 30% the year after, so on and so forth. And to do that, we need to develop interventions, i.e. solutions, and we need to come up with pathways for staging of them. So if that's the challenge, then when we look at which sector are contributing the large share of emissions, we'll see that buildings, they account for 50% of energy and around 30% of greenhouse gas emissions. Problems in buildings are that buildings are typically for longer, 40 years to 80 years, 100 years. Some of the buildings in Keynote are 100 years old. So buildings have a long lifespan. They are very diverse, small buildings, large buildings, single family dwellings, to multi-family dwellings, needs heating and cooling. And one interesting thing about buildings is that buildings affect our behavior, it influences our behavior, and we, in turn, determine how buildings are behaved, how buildings are run. Buildings depend on energy infrastructure. So energy infrastructure, we look at it, is generation, transmission, and distribution. So it's produced somewhere, transmitted, and then distributed by a low voltage and medium voltage grid. Transport, the bigger challenge for us is to how soon do we electrify transport? What sort of infrastructure we have? Electric vehicle, electric mobility needs its own infrastructure. And also travel choices. Again, buildings and transport of behavioral aspects. People are involved in that. Then we have another bigger sector is industry and water. How we are manufacturing, particularly process heat, where the heat is coming from, how is water treated and distributed. So if we look at those sectors individually, we will see that they are missing out on their interdependence. So if we look at building to energy grids, the demand pattern is determined by the characteristics of buildings. You know, how people use buildings, what we do, at what time we do what kind of activities, heat loads, grid constraints, so on and so forth. In the future, buildings will be linked with transport infrastructure. So eventually, our cars will be storing energy, which will then be exported to the grid when the grid needs it. So there is a link between our mobility solutions, cars, maybe buses, to the grid. So that's known as vehicle to grid. Demand response is another thing, is that we want to run things when low carbon energy sources are available. When sun is out, that's when we want to do most energy intensive activities. Energy has things with climate. So summertime, we do more cooling, wintertime, we do more heating. There's also cross-sectoral interdependence. So the reason for me to show all this is that we shouldn't just be considering every sector individually. We need to be studying or looking at cross-sectoral interdependence. And that's where techniques such as AI and machine learning can help us. So why should we model stuff? Model is the least cost way to develop a solution. We could build things, and then if it doesn't work, we could demolish it. It will cost us time, it will cost us money. So if we model things, we can test solutions fairly quickly, fairly easily, at the least cost. We could also study intervention impact. We could do infrastructure plan. So that's the challenge for sustainability. The scale could be bigger, the scale could be smaller or bigger. If we are talking about one building, the scale is smaller. If we are talking about cities, countries, nations, the scale will be bigger. So scale dictates what sort of modeling we can do. If we look at residential buildings as small scale commercial, and then when we group residential and commercial buildings together, we have a neighborhood. And when we combine a couple of neighborhoods, we get cities and regions. So complexities in modeling increases, right? Domain interdependence increases. So if we want to model a neighborhood, we obviously need to think about transport. If we are modeling one individual building, we don't need to model roads or transport. So your domain interdependence increases. Your computational cost increases as well. The bigger the model is, both in terms of scale and in terms of the domain it covers, it becomes more complex. You might also have data gaps. So a small building, we may be able to know a lot about that building. When you are talking about thousands and millions of buildings, it becomes difficult to capture those data. So when we look at modeling challenges, the scale for us, we think about nations, is that we have literally millions of buildings. We have data gaps and uncertainty, we have multi-physics complexity. So in a way, we have to model the microclimate as well as buildings if you're talking about neighborhoods and cities. Computational constraints are there. So you can't just ask a supercomputer, give millions of buildings, and then come back a year later with your results. We want our results fairly instantaneously. These are resource intensive as well. So what we will show in this presentation is that when scale is smaller, we go for engineering models. When scale is larger, we go for either statistical. We used to do statistical modeling before. Now we do machine learning mostly. So when I said larger models are multidisciplinary, these are some of the maps that shows. The first one shows by different infrastructure, energy is laid out in the UK. You can barely see the map of the UK, the borderline. That's roughly where major roads are. Most major infrastructure, energy infrastructure, are along major roads. So you see interconnection, grid interconnection with Ireland on the left-hand side, grid interconnection with Netherlands and Belgium, and France at the bottom. So we import electricity from all those countries. We also import gas. The middle one shows energy efficiency of domestic buildings. So band C is fairly average. So anything above band C, and you will see that there is a lot of, it's distributed quite widely. Some of the poorer regions, the buildings are not energy efficient. Buildings are not necessarily very sustainable. On the right-hand side, you see commercial buildings. So if you see yellow, that means it's energy efficient. If you see blue, that's less energy efficient. So in a way, we need to look at how the buildings are going to evolve to develop the infrastructure. So whether the infrastructure meets today's needs and whether we will be meeting tomorrow's infrastructure needs. So if we kind of summarize what those objectives are, those multidisciplinary objectives, is that the green ones are our objectives. We want to improve productivity, efficiency. We want to ensure that people are healthy and their well-being is maintained, resilience, net zero, and sustainability. But on the both sides, have your yellow ones. These are the challenges for those particular infrastructure. So power infrastructure, UK infrastructure is aging. One of the benefits of a developing country is that infrastructure is fairly new, whereas UK infrastructure, in most cases, it's 80, 100 years old. So you have to invest in new infrastructure. The climate change, interoperability, integration, demand generation mismatch, meaning that your energy is being generated at a time when energy is not used. On the other hand, in buildings, when we talk about the all 26 million homes in this map, is that they are energy inefficient. They are, people are changing their work patterns, meaning that they used to go to work, now they are working from home. A lot of people are working from home. We have special diversity and inequality, older building stock, so on and so forth, as well as aging population. So how do we model all of this? In the past, what we used to do is called physics-based whole building modeling. So essentially, in computer, just like you use your CAD program, we would be modeling the building in computer, which was resource intensive, meaning that a person would be spending anywhere between 15 days to a month to develop a small model, like you see in the picture. And what this model used to do is that we call it thermal heat transfer surfaces. So all of the heat transfer surfaces, walls, roofs, windows, floors, ceilings would be modeled. And so if I'm running this simulation for a whole year, every 15 minutes it would do the energy balance calculation, right? So if it does every 15 minutes, 15 times 8,760, so 8,760 hours in a day, and 15 minutes, so it's quite a large calculation process. It used to take us 20 minutes to 30 minutes, now it's down to 1 minute. So if you do this math, every building takes about roughly a minute, a house takes about a minute, and 24 million homes would take 24 million minutes for a home to be simulated just for one small problem. So it's computationally very expensive. And so on the right-hand side, bottom right-hand side, I'm talking about the process there. So your building is modeled in a simulation software. You have your boundary conditions, weather data, you have your occupant profile, so on and so forth. So this is a study we did some years back, where we looked at the performance of houses against climate change. So we were looking at houses, whether they are going to get overheated in the future. If they get overheated in the future, house design or houses may need to be refurbished nationally. So because it was computationally expensive, we would be running samples of simulation. So we have 1, 2, 3, 4, 5 different building typologies, 6 different building typologies, and different time periods to get a representative construction. So in total, we would be running about 430 simulations to get an idea what will happen in those buildings in now and let's just say 2100, in 100 years time or 80 years time. And why we did that, we wanted to design interventions from now, and we want to study the impact of resilience. So the right-hand side plots are climate plots, so different locations. EDI means Edinburgh, London means LON means London. So it's 6 different locations. So can you see that these are very crude way of estimating impact? We don't get to see the whole picture. But that was the state of the art, even 10, 15 years ago. And on the left-hand side, there are some plots to see what kind of buildings are going to get overheated. And you will see that the threshold, red line, is different for living room and bedroom. So living room, we can tolerate higher temperature for longer than in bedroom. You go to bedroom to go to sleep, and so there's only 33 hours during the summer period. UK summer period would be your whole year in Cardiff, but our summer is very short. It starts in August and ends in August. So 33 hours, not exceed more than that. And you will see that the buildings behave differently in different climates. And if you look at the bottom chart, where it shows the effects of different window opening, from 20% to 80%, and you will see that the about 58 buildings kind of exceed that threshold. So, the purpose of this slide is to show you that the old ways took time, and it didn't allow us to study a multiple disciplines, but it gave us an idea of what will happen in the future. So in here again, you will see that London is at the bottom and Edinburgh is at the top. The same way it's located geographically. London is in south and Edinburgh is top. London is hotter compared to Edinburgh. And you will see that 1990s is the left-hand side column, and 2080s is the right-hand side column. And all the interventions, the different interventions, whether people are opening windows, when they're opening it, does it cool the building down? And you will see that London gets overheated fairly quickly, maybe sooner than other regions or other areas in the UK. So physics-based model allows us to study the effects in more detail in an individual building, but that's not necessarily scalable. So let's take a look at a neighborhood solution. And in this exercise, in this project, what we tried to do is we tried to study the effect of distributed renewable energy generation. In each of those houses were having solar panels generating energy, what sort of impact it will have on the low voltage grid. So if you are pumping a lot more energy into your low voltage grid, that means the grid that runs around your neighborhood, then you will have problems such as overvoltage. So that's not safe for your electrical appliances. And this is what we call a multi-domain physics-based model. So multi-domain meaning that you have to model triple domain, your time-dependent domain, such as your voltage, your current, your energy flow, as well as thermal, because it is the thermal behavior of the building that dictates what sort of energy or how much will be needed at what time. So in the top right-hand corner, you'll see that there's a yellow curve. That's the solar energy generation, happens during the day. The magenta ones are the flexible consumption that you can move. So if you want to maximize the use of solar energy, then you will move it when solar energy is available. And you have your fixed consumption, that's the blue one. So the conclusion of the study was that if you do not have an intelligent energy management system within neighborhoods, then when solar penetration exceeds 40%, meaning that if more than 40% of houses have solar, then on certain days your grid constraints will not be met. So grid constraint meaning that your voltage, so that's roughly around 400 volts, that the red line will not be met, right? So your thermal behavior is affecting your electrical domain problem or electrical domain objectives. So that's the second example, is that we can then scale it up to multi-domain physics-based modeling. Again, it took us a lot of time both to develop the model as well as to study it. So then within the same neighborhood where the project was, we then started experimenting with augmenting machine learning. So that's roughly 10 years ago. What we did. So in the middle, we still have our energy simulation program that is physics-based. It's a long time. A lot of the boundary conditions was that we were not necessarily modeling it based on actual people behavior. So if I kind of explain the occupancy probability on the right-hand side, you will see that the green one is what we used to do. We used to assume that people will be leaving for work around 8-ish and come back at around 6-ish. But that doesn't happen in every household, right? And that doesn't happen every day, even people who are working. So that is the probabilistic thing. And how can we do that? So we introduced statistical-based modeling to predict occupant behaviors and devices usage. These plots are on the impact of how different appliances are kind of modeled based on probability. And if you want to work with statistical or machine learning models, then you would have to have access to a large amount of data. Luckily, the UK had done a significant amount of work around understanding what people do in their house. So we took data from that. So this is an example of how you can augment machine learning and statistical modeling into your physics-based simulation. The third one was that it's not a step up, but it's a lateral direction. So up until now, we were mostly talking about planning, meaning that I'm designing an intervention. I want to test those interventions. But can I use those techniques in running buildings? So this is a commercial building in Barcelona. It was again part of the project. And so we wanted to apply machine learning to run the indoor HVAC units. So there are 9 HVAC units in this floor, and it's a technical model predictive control. It's nothing new. What's innovative in there is that instead of using a physics-based simulation, we wanted to mimic the effects of physics-based simulation using machine learning. And on the right-hand side, you have your temperature plots for each of those units, the modes, meaning H means heating, C means cooling, and the set point. So set point is the temperature above or below which your heating or cooling system turns on. So if you look at your air conditioning at home, it doesn't run 24 hours. It runs when it exceeds a certain temperature. And you will see that the blue ones are the actual operation and the orange ones are the MDC ones. So on the whole, orange ones operated much better. And another thing in this particular research, the machine learning allowed us to have is that every 15 minutes, it would be deciding what's going to happen in the next 24 hours. So it's a day-ahead optimization problem. So every 15 minutes is deciding, I will turn the AC on 4 hours later, 6 hours later. So you have to do all your calculations. The machines have to do all the calculations within 15 minutes. And that's thousands of simulations. So if you multiply thousands by 1 minute, you need 1,000 minutes for a computer to run one optimization problem. Whereas machine learning allowed us to do that in embedded systems. So machine learning simplifies the problem domain while keeping the most important parameters, while making sure that the relationship between the most important parameters are retained. Well, if you develop the model well. Now, let's take a look at other kinds of problems. So this is a research we're still working on, is a national model for Turkey. So Turkey wants to decarbonize as well. And you will see that the demand centers in Turkey and kind of renewable energy that's available do not necessarily match. So Istanbul, top left-hand side, that's where the majority of the demand is. But most solar energy is available in the south. Right? So demand and your generation not much. And you will also see that the Turkey as a middle-income country, their energy demand is rising. Energy demand is going to continue to rise. So what we need to study, or what we need to identify, is where those demand hotspots are, and identify why demand is increasing, so that you can either generate energy to meet that demand, or address the issues that's causing the demand to rise. And so this is a fully machine learning based model. We had done similar work in Bangladesh, 2050 model, and those were mostly engineering models. And another problem with long horizon future energy modeling is that your input also needs to be forecasted. So we go back, I'll come back to this in a minute. So that's the projection for province-wide projection between 2010 and 2050. So 2010 to 2023 is the actual data that's in black. Everything else is projected. So when you do that projection, then what are the parameters that affect demand? So what we found is that population, GDP, economic activity, a proxy of economic activity, and household characteristics are stronger predictors than climate variables. So you might think that, okay, world is warming, so there must be more cooling, energy for cooling. They do, but it's the population and the households are the bigger driver. If that's the case, then if we want to predict what's going to happen in 2050, we also need to know what the population will be in 2050. Not only that, we also need to know what the distribution of the population will be. So will there be aging population? If they're elderly, they will be spending more time in the house. If they're young, they will be out and about working. So we need to know that. And in climate circles, there's a concept called SSP. And SSPs are pathways that is kind of break up based on the societal direction. The society is going towards a sustainable pathway, or the society is going towards a fossil fuel-driven kind of development. So different SSPs are predicted in here, and machine learning allowed us to do that. How do we know that machine learning models were better or worse? So we compared it with the kind of model that we used to use for linear model, and we compared it against linear models, and we compared it with other types of models. And that exceeds the threshold of acceptability, both in terms of error metrics and the utility of the predictions. Not only that, we're able to predict what's going to happen in the future, that's the strength of machine learning, but also the data for each of those provinces are only 10 data points. So when you multiply that by 81 provinces, that's good enough data, or significant enough data for us to do machine learning training. So currently we're working with the Ministry of Electricity in Turkey. Currently we are developing a gas model. So the next one is that the sixth iteration is that when we were developing all of those models, we then ask ourselves this question, is that when we model a building, how do we know that that building is representative? So Kiritaro, it has 100,000 buildings, and we're only modeling 1,000. How do we know that 1,000 buildings represents all of the 100,000 buildings? So in machine learning, clustering is a concept, clustering is a technique that's quite commonly used to group things together, to group similar things together. So we developed a technique called MSF, minimum segmentation frequency. If anyone has a question, I'll go into details later. To have representative modeling. So even when you are doing physics-based modeling, or even when you are doing machine learning models, then you've got to ensure that it's well represented. So here we have our MSF 15, so that's our algorithm on the left-hand side. And English Housing Survey, that's the middle column. And if we do clustering with that minimum segmentation frequency, we get the right-hand side. And you will see that the distributions are widely different. So just because clustering is there, and you apply clustering, doesn't necessarily mean that you're not doing the right thing. So when I first started my presentation, I said that when you are modeling national energy or sustainability model, you need to consider multiple domains. So this is what we did for world government. So we developed an integrated model for the whole country. And so when we looked at the country, we divided it into different sectors. We have your supply sector, that's in orange. And you have your demand sector, that's in blue. So supply side, you have renewable power and heat, power hydrocarbon. You also do balancing, import and export, storage, so on and so forth. In the demand side, you have your agriculture, domestic, commercial, transport industry, aviation. Now, Wales has some similarity with Mexico in the sense that agriculture is a big part of Welsh life. So livestock, for example, a lot of UK livestock happens in Wales. So land use and waste is another area that you have to consider. So the idea is that you develop an engineering model along those lines. So imagine you have a GIS-based model for every district, for every postcode, and then you try and model demand, and you try and see where the demand is going to come from.
So those engineering models, the next iteration, what we did is we replaced a lot of the engineering models with machine learning. Because machine learning allows you to develop a population-based model or population-dependent model, where you can study and test different scenarios. So I think this is probably my last slide as methodology, is that the household characteristics that I talked before, population, for example, all of those are modeled based on neural nets. The property survey will apply clustering that gives you how many houses you need to model, and that all feeds into, when you combine building physics with machine learning that predicts the boundaries, then you have a model that can extend beyond present day to sometime in the future, 2050. There is nothing stopping you to go up to 2100. And so if I kind of summarize all of this, that from physics-based model to AI-driven digital twins, the two things that pop out, one is the scale of it, what exactly you are modeling, what is your objective. That kind of determines methods of modeling. So we started with physics-based modeling. We had 432 runs. Then we looked at multi-domain physics, where we had to model electrical domain as well as thermal domain. Then we augmented machine learning, hybridizing it to part of the model becomes an ML model. And then we looked at ML-based control, and then we are looking at pure ML that helps us determine or predict future energy demand. So scale dictates approach, to summarize those key insights, and no single method can actually meet all of the objectives or all of the demands. AI enables what physics cannot. Why is that? Is that we are not population scientists, but we are able to take the knowledge from population science, from demographics, and enhance our engineering model. And that's the beauty of machine learning, is that we don't have to know a lot of things. We need to know what affects what, then we can account for it in our work. And that's true not just for engineering, other disciplines of science, where you don't necessarily have to have well-developed knowledge in a particular domain. You can still consider it in your work. So what's next for us? There's a lot of uncertainty still. You remember one model, the R squared was around 0.93. So there's a little bit of uncertainty there, so we need to improve on that. We also need to improve input forecasting, particularly for long horizon models. Physics-informed model has a lot of development needs to be there. And one particular machine learning technique that we are working on is called scenario-based machine learning. So we haven't yet published on that. We are getting there. Multi-domain modeling, and the aspect that engineers should consider social science into their work. And machine learning allows us to do integration with utility grids, with transport infrastructure, as well as urban mapping for microclimate. We still are using cruder climate model for a lot of our work. So our data comes from nearby airports, but because of urban heat island, the temperature profile is very different in cities and the weather data that comes from stations. So that's where we like to work. Data infrastructure and access infrastructure and downstream accessibility to make it more open. So what I tried to do is I tried to show you the evolution where I started with engineering models, let's say brick and mortar models, to more advanced models, AI and machine learning. Some people would call AI advanced models because a lot of it is black box, don't know what's happening, but at the same time it's very powerful.
Thank you. I'm happy to take any questions.
We have not had a Q&A session with Professor Monjur. Anyone have a question?
Hello. How is the, for example, the model will change when, because in the future we will have a vehicles, so station grid vehicles will increase the demand at the night. So how your model will be robust for those changes that are not considered now because the electric mobility is very low in comparison with the future days. So how it should be, or how robust? That's a very interesting question. It depends on what is the objective of your model. If your model's objective is energy planning, so let's just say I want to identify how many new power plants I need to create. That's an energy planning problem, right? So you look at more capacity. But if you are looking at, okay, do I need to change the power distribution lines? Do I need to change transformers? Do I need to installing improved devices, voltage control, for example? Then you are looking at electrical domain modeling. And so depending on the objective, the modeling paradigm will change. Regardless of whatever we want to use, the future will be physics-based and machine learning. The specific answer to your question is that whether if I understood it correctly, is that vehicle-to-grid problem, whether it's going to be at night, whether it's going to be at day, that's going to be dependent on the season. That's going to be dependent on a country's tariff structure. So we are talking about France, for example. France depends on a lot of nuclear power. So that means their baseline is fairly stable. So if their baseline is fairly stable, what they will do, they will design the tariff in such a way that people will be shifting their heavy energy consumption to periods when the grid doesn't have a significant load. So the answer to this question will be different for different countries.
Another question?
Thank you for your talk. Very interesting subject. I don't know, how do you verify your simulations, your sources of simulation, to predict the results that you are getting? How do you check?
So, physics-based simulation, we do monitoring. We model this building, we will monitor all the energy circuits. So, the distribution board, we will install energy monitors. So, we will be getting energy data for 1 different minute in 5 minutes. And we run this simulation based on the weather that the building experienced, and if the results match within a certain uncertainty range, then we say that, okay, model it perfectly. But the word perfectly is where the question is, because a building's energy consumption is very much dependent on how people use it. Right? Think about your office space. You model that, okay, people go into the office, come out of the office, everything is switched off. But it's not. The computer is still working. Your lights may be on, your other appliances may be on. So it's those stochastic behavior that is different.
That seems like very easy or more simple to check the simulation against the results in a building. But how about in a big city?
Oh, big city in the UK, we are fortunate enough that we get energy consumption data, half-hourly energy consumption data. smart meter data. We get smart meter data for any building we want to. So all 29 million domestic customers, every half an hour, the data gets reported. Not all 29 million, but roughly more, around in the same time. So we get that data. The other way to kind of validate your model is, you can do Monte Carlo simulation to change those parameters. And when your model kind of outputs within the range that you find acceptable, then you say that, okay, that's an acceptable model. So there are many different techniques of doing that. But when we work in Turkey, when we worked in Bangladesh, we didn't have that high resolution data, where we had to apply other techniques. So, backwards tracing, Monte Carlo simulation to validate our model.
We have a brief time to another question.
Thank you, Professor Monjur, for your presentation. Usually, the quality of energy is different from country. I would like to know how it is introduced to your model this.
So the 7 different examples that I think it's when we were doing electrothermal simulation, that's when we looked at quality of supply. All the other models, we didn't look at the quality. Because to do quality modeling, you would have to model the infrastructure, electricity infrastructure itself. That's a kind of a problem. It's more computationally intensive. So again, what I was saying is that it depends on what is the objective of your modeling exercise. If it's intervention design, particularly for quality of supply, then it has to be done. In the UK and in Europe, the suppliers are mandated to maintain the quality of supply. If they do not maintain the quality of supply, they get fined. The energy market is decentralized and deregulated, which may not necessarily be the case. It wasn't the case in Turkey. I'm 100% sure about that. So if energy market is not deregulated completely, then we don't have those mandates to go after the utility companies if they do not meet the quality criteria. Thank you. Thank you all for your time. Thank you.
We did this gratitude for your distinguished participation. The organizing committee is honored to give you this token of participation.
Hola, hola. Bueno, pues vamos a acercarnos un poquito más al frente. Ya estamos en la parte final de este congreso. Ya estamos por cerrar. Estamos muy emocionados todos. Entonces, los invitamos a acercarse. Vamos a iniciar con la ceremonia de cierre y premiación. Entonces, por ahí, por favor, vénganse para enfrente. Denos unos 5 minutitos para detalles, pero ya vamos a iniciar.
Yeah.
Bueno, pues buenas tardes a todas y a todos. Muchísimas gracias por acompañarnos. Sé que ha sido una jornada muy larga. Sé que estamos cansados, pero pues les agradecemos muchísimo que nos hayan acompañado a lo largo de estos 3 días. Les recuerdo brevemente que ICASAT es un congreso que pues está hecho con la colaboración de muchas personas, de estudiantes en particular del ICASAT. Y entonces, bueno, estuvimos 3 días, tuvimos muchísimos ponentes y pues bueno, llegó la mejor parte, en la parte de las premiaciones. Entonces, vamos a iniciar con esta ceremonia. Voy a iniciar con la parte de los pósters. Es para mí un placer comentarles que tuvimos muchísima participación. Gracias a todos los autores que estuvieron en el Congreso para presentar sus trabajos. Como pudieron ver, hay trabajos de muchísimas áreas porque parte de este congreso es que es un centro, nosotros somos parte de un centro multidisciplinario y pues hay áreas de biotecnología, computadora, entonces materiales, ciencia artificial, pero todos pues, los trabajos están enfocados de cierta forma pues, a resolver las problemáticas que nos atañen el día de hoy. Les quiero comentar que tuvimos la participación de 31 pósters. Por ahí asistieron una buena idea de ellos por la tarde. El primer día pues, pudieron interactuar con los ponentes. Durante estas sesiones teníamos diversos jueces. Bueno, los autores no sabían quién los iba a evaluar, entonces pues ellos tuvieron que presentar a diversas personas y de ellos pues, o varios de ellos pues los evaluaron. Entonces, de ahí se hizo una rúbrica y de esa rúbrica pues se eligió al mejor trabajo. Estos jueces pues fueron invitados externos, invitados del ICASAT, doctores, maestros que nos ayudaron en esta evaluación. Y bueno, también me complace informarles que estos pósters no nada más quedaron aquí en el evento, van a estar publicados en nuestra página web, por si por ahí les interesó alguno, no pudieron ver al autor, pues por ahí pueden volver a buscar y buscar a quien les interesó y a lo mejor contactarlo y seguir pues esta colaboración. Bueno, y en el momento de reconocer a los autores del mejor póster, pasen por, bueno, los premios del mejor póster. Ellos son nuestro grupo de chicos que nos van a ayudar a entregar el premio. La ganadora del mejor póster es Leticia Saraí Morocho López. Está por aquí. Bueno, es una biomáquina. Por favor. Gracias, gracias.
¿Qué tal? Buenas tardes. A mí me tocó presentar a la mejor presentación oral. En este caso, se seleccionó, obviamente también por un proceso en el que hubo evaluadores. Se seleccionó aquella ponencia que expresó de mejor manera el contenido de su proyecto de investigación. La divulgación es un concepto que en ocasiones puede ser complejo para algunos de nosotros, para otros quizás no tanto. Sin embargo, pues es enriquecedor este tipo de eventos, ya que nos permite justamente trasladar esos conceptos técnicos a un público que quizás no sea de nuestra misma área. Entonces, esta presentación, en este caso se valoraron aspectos como la claridad de la presentación, el dominio del tema, la originalidad de los resultados, la capacidad de transmitir el conocimiento a la audiencia. En este caso, la mejor ponencia magistral es para Alfredo Puentes Flores. Su ponencia fue para Making of a Soft Robotic Reaper for Orbital Classroom. Démosle un segundo aplauso.
Ahora damos continuidad y para finalizar, el mejor paper. A lo largo de estos meses, el comité organizador ha llevado a cabo un proceso de evaluación completamente imparcial, garantizando la calidad y la equidad en cada etapa. Este proceso fue posible gracias a la invaluable trabajo alrededor de 60 revisores que tuvimos, provenientes de diversas instituciones nacionales e internacionales, quienes dedicaron su tiempo y experiencia para revisar cada uno de los criterios y los artículos recibidos. Cabe destacar que todas las evaluaciones se realizaron bajo el formato de revisión por pares. Gracias a este esfuerzo conjunto, hoy podemos conocer los trabajos que nos destacan por su rigor científico, sino también por su originalidad y contribución al avance del conocimiento aplicado. Asimismo, es importante mencionar que todos los artículos afectados serán publicados por las memorias de Springer del Congreso, las cuales estarán disponibles en unos meses. Y ahora sí, llegando al mejor momento. El premio para mejor paper es para Isolation Identification of Potential Probiotic Enzymes por la doctora Regina Hernández Gama y María del Rosario. Para continuar, nuestra presidenta del comité organizador nos dará unas palabras.
Antes que nada, me gustaría que pudieran tomarnos los tres ganadores para tenerlos como referencia para el proceso. Si pudieran pasar nuevamente con su recreo. Alfredo. Yo creo que cada una de las actividades que hubo en el Congreso requirió de un gran esfuerzo. El proceso editorial fue un proceso bastante largo. El deadline fue en julio, entonces todo julio, agosto, septiembre, octubre, pues fue de apelaciones, de solicitantes a los autores que hicieran las peticiones que solicitaba el profesor. Entonces yo creo que cada uno de ellos se merece un enorme aplauso de parte de nosotros. Y por otro lado, es importante agradecer el trabajo de cada uno de los organizadores de este congreso, ya que pareciera curioso, pero literal, el comité organizador salió de una plática en el comedor que tenemos a las 12 de la tarde en ICASAT, en el que se seleccionó, en el que curiosamente Ángel dijo quién va a echar el paquete de hacer el ICASAT este año. Literal, así salió el comité organizador. En este caso, me pusieron como dedazo, pero fue muy bastante. Tal manera que me gustaría presentar orgullosamente al comité organizador, que está integrado por estudiantes de maestría, por estudiantes de doctorado, y voy presentándolos, ¿no? Se me acuerdan los nombres. Bueno, empezamos con nuestro comité editorial, en este caso liderado por el maestro Ravela. Este comité editorial estuvo integrado también por Carmen Peregrino, por la maestra Por otro lado, muchas de las actividades tuvieron, por ejemplo, ya estuvo integrando dos comisiones, en este caso, la comisión también de difusión, la página web en la que hemos estado trabajando prácticamente de un año, llenándola de contenido, la trabajó Caja en conjunto con otras chicas de maestría bastante entusiastas, con una creatividad inmensa que todos pudimos ver en estas pantallas. Justo ahora estamos viendo la creatividad que tienen nuestras chicas. No contratamos un grupo de diseñadores, realmente nuestros estudiantes de grado pudieron abrir su creatividad para que nosotros ver todo este contenido. En este caso, este grupo fue integrado por Luana, la ingeniera Ravela, por la educación y por la institución de los adultos. Por otro lado, también tenemos el área de logística. El área de logística le toca ver todo lo que es la calidad de la. En este caso, tenemos nuestro líder fue el maestro Ángel. Bueno, nos pidió que pudiera cancelar este evento, entonces le debemos mucho al compañero Cardiff. Estuvo integrada esta área de logística por Toño, por Dani, por Sergio, por acá por el compañero Márquez y por nuestra compañera Betty. Y la verdad es que me gustaría ofrecerles unas palabras de agradecimiento. Oliva, ¿dónde está Oliva? Bueno. Oliva. Hoy estuvimos disfrutando de diferentes actividades, entre estas incluidas algunos workshops. Esos workshops estuvieron coordinados por la maestra Oliva. En este caso, pues, cada uno de las personas que estuvieron apoyando. La plataforma de internet a las 9 de la mañana para empezar los talleres fue Oliva. La verdad es que estamos Le damos un enorme abrazo al presidente que está presente. Por otro lado, también hubo profesores que nos apoyaron en el comité editorial, en este caso un reconocimiento enorme al doctor Joaquín Salas, que fue nuestro coach en el comité editorial, adicional al doctor Ravela de la Universidad de Cardiff, que integra el comité editorial. También hay que mencionar el apoyo de profesores como el doctor Juan, nuestro director, a la maestra Edith, que nos estuvo apoyando literalmente desde que empezó el congreso y todo lo que necesitábamos, viendo los mensajes en la prácticamente en la noche. Y no está de más agradecer a todos los profesores de ICASAT que hoy estuvieron participando en las actividades. He visto al doctor Rubén que participó desde el día miércoles temprano, al doctor Puerta, al doctor Pablo, y a la doctora Marlene, a la doctora Regina con sus preguntas. La verdad es que ha sido una actividad muy emocionante, muy divertida. También el doctor Iván que estuvo desde el miércoles muy temprano. A Ale, que nos estuvo apoyando en las transmisiones en vivo, ella también nos apoyó en el diseño de la página web oficial de ICASAT, a los estudiantes que estuvieron participando en estas actividades. En fin, son muchísimas personas las que nos estuvieron apoyando. Y por otro lado también a los talleristas, a todas aquellas personas que en algún momento no pudimos asistir a alguna clase porque salió algo de improviso de ICASAT. También a los Keynote speakers que en este caso pues, nos cobraron realmente fue una invitación que les hacemos y afortunadamente ellos se sientan venir con nosotros para contarnos un poquito de lo que hacen. Por otro lado, también quisiéramos agradecer aquí al péndulo, al personal del péndulo, que nos ha estado atendiendo prácticamente desde el día martes, que fue el montaje de todo el mobiliario aquí en su establecimiento. Nos han dado el apoyo al 100%. Ahorita no los ubico, pero por mencionar algunos, allá tenemos en cabina a Ale, que ahorita nos va a apoyar con una producción. También tenemos a la señora Gabriela, que es la encargada de aquí planetario, que fue del área de difusión de ciencia y tecnología de Concitec. Y también tenemos a Dianita, que anda desaparecida por andar. Por otro lado, también me gustaría invitar a los chicos de staff que se la rifaron en estos 3 días, apoyando el coffee break, en todo lo que fue necesario. Si hay alguno todavía por aquí, me gustaría que los pudieran conocer. Y finalmente, el reconocimiento institucional. Le damos muchas gracias al Consejo de Ciencia del Estado de Querétaro, a la Secretaría de Turismo y a la Secretaría de Cultura, que también estuvieron apoyándonos ayer en actividades organizadas por la Secretaría de Turismo y ahora en nuestro nacional organizado en el claustro de Santa Rosa de Viterbo, sede de la Secretaría de Cultura. Y solo quisiera mencionar lo siguiente. Solo quiero agradecer al equipo de ICASAT por su profesionalismo, su entrega y sobre todo por ser prestaciones increíbles. Cada uno tiene sus talentos y no tuvimos que aprender a pintar las plantas. Ya vienen integradas con ellos. Solamente puedo obtener ese talento y disfrutar el proceso. Divertido, retador, lleno de aprendizajes, que me permitió conocerlos más y valorar profundamente su vida. Espero que algún día volver a coincidir con ustedes. Será sin duda un honor para mí. Muchas gracias.
Muchas gracias, Ravela. Gracias a todos los jóvenes por concederme el honor de cerrar este evento. Así como funcionaron en estos días, así queremos que funcione la investigación. ¿Verdad? que se den cuenta que las cosas salen mucho mejor cuando las hacemos, pues también aceptando, ¿no? Cada quien tiene su función, no andamos peleando protagonismo ni quedar al frente ni nada, sino que sabemos que el trabajo de cada uno de nosotros es importante para este proyecto y para cualquier otro que nos propongamos en la vida. Entonces, nada más me queda agradecerles todo su trabajo, desearles que en el futuro este aprendizaje les sirva para crecer y ser grandes investigadores en México, que tanto lo necesita. Entonces, pues nada más me voy a permitir, siendo las 5:28 del 2025, damos por terminados los trabajos extraordinarios de este cuarto Congreso ICASAT 2025. Los esperamos dentro de 2 años. Corran la voz, díganles que este evento está creciendo mucho y que nuestros talentosos jóvenes investigadores hacen un trabajo extraordinario. Muchas gracias a todos.